Okay, so very good morning, everybody. Deepak, we can start the recording. Okay. Okay, so very good morning from FOSSI IIT Bombay. And I'm Payal Mukherjee once again. Welcoming you.
Oh, madam, just wait for 1 or 2 minutes. Some
Okay.
technical glitch is there. So
Okay. So
just
you let
two
me know
minutes.
when to start.
Okay.
Okay, till then, we can just interact with the participants, whoever has joined now. Any questions for us? Any doubts?
Yeah, we are live on YouTube.
Okay, we are live. Okay, fine. Okay, so welcome everybody. A very good morning from FOSSI IIT Bombay. I am Payal Mukherjee, working as Senior Project Manager at FOSSI. And it's the day 2 of the very exciting and informative workshop that we are having now, the Industry Readiness Workshop on CFD. So as you all know, during these 4 days of the workshop, we'll have live lectures by the CFD professionals who are the esteemed member of the advisory board of the CFD team of FOSSI. And yes, good morning. Yeah, and so all of them, they will come. The 6 of them actually, they'll come and interact with you. They'll share their experiences in their professional career, and it is going to be a very informative and also interactive workshop. So after the talk session of all the speakers, you'll get the opportunity to interact with them, to ask them questions. And today we are going to have the first lecture by Mr. Arnab Chakrabarty. So welcome, Mr. Arnab Chakrabarty, and thanks a lot for joining today. So let me just briefly introduce Mr. Chakrabarty, and then we can move ahead.
Yeah, before that, I'm having a request.
Yes.
Okay, the sharing option was not there. Now it is coming. Fine, you can go ahead.
Okay, fine, thank you.
My slides are visible?
Yes, your slides are visible.
Okay, thanks. Go ahead.
Yeah. So let me first introduce Mr. Chakrabarty, and then we will hand it over to him for his session. So Mr. Arnab Chakrabarty has done his MTech in Ocean Engineering and Naval Architecture from IIT Kharagpur, and an MS by Research in Mechanical Engineering Thermal from IIT Madras. He has previously been an SN Bose Scholar at Texas A&M University, and a VSRP fellow at the Clean Combustion Research Group at KAUST Kaust, Saudi Arabia. He has received internship awards from the Indian Academy of Science at IISc, IIT Madras, and IIT Gandhinagar. He has been honored with the Indian National Academy of Engineering Innovative Project Award by the Department of Science and Technology, DST, of the Government of India, a prestigious accolade given to only 8 individuals nationwide, and the sole recipient from IIT Madras and West Bengal. Additionally, Mr. Chakrabarty has worked as a simulation engineer at Immersion Process Management and as a fluid mechanics consultant at Analytics Plus Incorporated. He has authored 7 journal articles, 30 conference papers, and 5 book chapters. Mr. Arnab has also served as a reviewer for the esteemed journals such as Physics of Fluid, Atomization, and Sprays, and IMechE, and conferences including FMFP, ASME, Gas Turbine India, GT India, and ASME. So we are really fortunate. We are really thankful to have Mr. Arnab today as a guest speaker in this workshop. And I hope his session will be a very useful one, very informative and effective one for all the students, faculty members, as well as the CFD professionals who have joined today. So Mr. Arnab, actually the audience is a mixed crowd. Majority of them are students, and some of them are also faculty members, and a few of them are from the CFD professional background as well. So over to you. You can start the session today.
Okay, thank you, Pal, for the nice introduction. So, as you can see my presentation, the slides are changing.
No, actually, I think you'll have to do the full
Now it
screen.
is changing.
Now it is changing, but it is not in full screen mode.
That is fine. That is
Okay.
Yeah.
Yes,
Okay.
now it is in full screen mode and it's changing also.
Fine. Thank you. So, okay. So thank you, Pal, for the nice introduction. So, yeah. So today, I'll show the different sides of the droplet dynamics, which are very relevant in nature as well as in the industry. So that's why I kept the name purposefully, that the droplet dynamics across the spectrum from traditional CFD to modern molecular simulations and ML-based models. So the intention of this talk is not to show the detailed numerical simulations. Here, my intention is to give you an overview that what kind of work we are doing in presently in the TCS research, as well as uh, uh, the state of art, what people are doing on the across the globe on this domain, and what are the possibilities, what are the scope you can work on or you can think upon. So yeah, so I myself, Arnab Chakraborty, uh, I'm working as a scientist in TCS Research, that is the Tata Consultancy Services Limited R&D. And here, our team basically deals with different multi-phase flow problems across all domains, from the chemical processing industry, aerospace, the ocean or atmospheric sciences, the climate change, um, etc. So, yeah. So the overview of the talk will be the background. I will share basically the three individual case studies to give you an overview. So some of the studies, the most part of the this talk will be on CFD, and after acquiring the data, CFD data, we did some machine learning, and as you know, the CFD and all other mesh-based methods, and finally I'll touch upon the meshless methods or the molecular level simulations of the same thing to give you an overall idea and the differences between the CFD and molecular dynamics and how those are useful and etc. So let's coming to the talk. The overview of the talk is will be the background. I will discuss briefly the background of each of the problem associated with the respective case studies, then the novelty and objectives, then the computational setup and validation of the model, then the modeling of the spreading parameter, that is an image processing based approach. So there are many approach. I will mostly focus on the image processing based approach, and then we did several variations. Those are the parametric studies, that is the effect of impact velocities, inclination angle, static contact angle, etc. And then the effect of non-sphericity of the droplet on its spreading, and the machine learning in droplet dynamics, and then I'll conclude. So before going into the simulations or the studies, first let us see the background. Okay, so droplet, the um, application of the droplet dynamics could be found in nature as well as industry, as I already mentioned. So in nature, in many aspects, these problems are useful. Let's say a droplet is impacting on a leaf, okay, and that droplet carries certain amount of bacteria. So upon impact, the droplet will spread, right? So it will spread the disease also. So based upon its maximum spreading, one can predict that how much the disease can spread within that residence time. It means the droplet impacts and it leaves the surface. Okay, in between this time is called the residence time or contact time, whatever. So yeah, in the in another example, you can see during the COVID transmission, we were very obsessed with the droplet, and even though apart from apart from COVID, there are many other disease that can be transferred or that transferred using the droplets, basically. And uh, and you don't know how they will spread. Even nowadays, the recent study shows uh, the this urinary tract infection that is very prominent in the young woman, that is also spread due to the droplet transmission in the public toilets. Okay, so that is why uh, it's dynamic, how it evolves with time when it interacts with the surface is very important to study. And further, this droplet dynamics is having application in changing the local climate. Let's say when a wave breaks in the shoreline. Okay, so it produce very fine droplets, and due to the temperature and humidity and other stuff, that those droplets gets evaporated and change the dryness fraction of that local area, and eventually that contributes to the climate change. Further, let's say when a flight is going through the cloud or going through the volcanic ashes, okay, those if it is going through the cloud droplet usually interact with the this compressor blade, and if it is a volcanic ashes, eventually sometimes the metallic droplet, the liquid molten metal droplets uh, just comes and hit the compressor blade, and is having uh, mm, several consequences, like the imbalance in the rotating machinery, like compressor and all, and then its erosion, uh, and if that droplet is reacting with the blade material, then corrosion. Okay, so eventually it is and rain droplet impact on the wind turbine blades. Okay, so eventually the how the droplet interact, or how the droplet what could be the dynamics of the droplet upon impacting on several test cases, whether it is compressor blade or whether it is wind turbine blades, or it is fixed surface. um, it is important to study to understand the dynamics. So every time the dynamics changes with time, and it varies case to case basis, so there is no direct correlation exist among the all cases. um, so this is the case study one. Now coming to the case study one, as I said, I will show three different case studies, and uh, you will see the differences. So this is the first case study, that is yeah. So that is the numerical simulation of post-impact dynamics of a droplet on an inclined surface. Okay, so these are the lacuna of the literature. Uh, as you can see, yeah. So it is imperative to mention that most of the studies were experimental, and most recent studies among all reported literature are up to the inclined plane 60 degrees, but we have extended our study up to 75 degrees. Okay. So it could be observed from the few numerical studies that the dynamic of the droplet changes in the tangential direction above 70 degrees, while there is no mention of the post-impact dynamics of the lateral post-impact dynamics of the droplet on in the lateral dimension. This means that when the droplet is impacting on the inclined surface, eventually, although the droplet was initially was spherical, but when it spreads over the inclined surface, it is having two spreading parameter. One is along the axis, or along the motion, and the motion or along the axis, that is your longitudinal, and one is the in the lateral dimension. So most of the previous studies mentioned about this longitudinal uh, or along this axial spreading, but there is no mention in the lateral spreading dimension, because that is also important in certain applications like coating, spray drying, painting, 3D printing, etc. So we have reported the lateral dimensions also, and we try to correlate this lateral dimension with the axial dimensions. Um, all previous studies were focused mainly on the rebound and splashing regime, whereas there is a substantial gap in the literature for the deposition regime, which is having direct implementation in spray painting, tablet coating, 3D printing, and metal additive manufacturing. Okay, all the previous studies talked about the dynamics of the spherical droplet only. However, if the droplet is larger, uh, or uh, or if they are a polymeric droplet, they multiple times they cannot sustain their sphericity, and they becomes non-spherical while impacting. So there is no literature available that discuss the dynamics of the non-spherical droplet upon impact. And uh, so droplet compressor blade interaction, or droplet turbine blade interaction, or whatever droplet and any rotating parts, rotating machinery is a major issue which need to be addressed. And yeah, there are very few machine learning models available for predicting the droplet dynamics upon impingement. So mostly, if you see the literature, all those machine learning models are applicable for very basic test cases, like droplet is impacting on some smooth plain surface kind of stuff. But when so as you know, in the machine learning we usually give some input parameters and we expect something at output. So let's talk in a layman's term. So if you are giving some inputs, so if you are increasing the complexity of the problem, like if you are giving the inclination angle, or heat transfer parameters, or the rotational motion, or the translational motion, whatever the input parameters, eventually it is the complexity increases to train the machine learning models. Okay, and at the same time the computational cost also increases, and the and if your data set is not adequate, eventually the convergence issues also come. There are several reasons for that. The people have started with the sample cases, but we will show you some complex one. And another thing is that uh, nowadays machine learning is evolving in across all domains. Okay, so it is very important to consider as a very useful tool, because the CFD simulations, each of the, depending upon the grids and other things, the machine configuration, etc. The CFD simulations usually takes lots of times. Let's say for our case, for a single case study, uh, let's say a droplet is impacting on an inclined plane, and you are using 12 lakh grids, 12 lakh to 15 lakhs grids, uh, and it usually takes 10 hours. So yeah, in a 8 core processor, let's say, sorry, 8 GB RAM, so it usually takes 10 hours. Okay, so eventually every day we usually runs thousands of simulations in the industry, so it is not possible so to run every time the CFD simulation. So what we do, we usually run the simulations, and whatever we have performed the simulations in the last few years. So based on those data, we try to develop the machine learning model so that they can able to predict precisely, or within the specified accuracy, let's say within 80% or 90%, the actual dynamics, so that we can save a lots of time effort as well as the computational cost. So that's why the machine learning models are very useful nowadays for modeling these multi-phase flows or these droplet dynamics, whatever. And yeah, there are very limited numerical studies available for the dynamics of the droplet on a plane having different motion. So if you see the literature, multiple you will find the problems associated with the droplet dynamics on the fixed surface. But once you are considering the moving surface, let's say the droplet is impacting on some unidirectionally translating motion or some vibrating motion or the rotation or the combined of any of these motions, eventually uh, hello.
Yes, you are audible.
Okay, so I saw someone raise the hand, so let me finish and then we can take the questions. Okay.
Sure, sir.
Okay. Yeah, so eventually, if you introduce the motion on the surface, the problem becomes more complicated, and eventually, for these kind of problems, these droplet dynamics kind of problems, so it is uh, very important to track the triple phase contact line. Means um, where that when the droplet touches the surface, eventually with time it will spread, right? It will spread, it will reach its maximum spreading limit, and then it will start to recede, and then it will jump off from the surface in case of rebound, and or it will splash eventually uh, if the impact velocity is very high, and if impact velocity is very low, it will deposit, it won't rebound. So eventually so in all cases it is very important to track the triple phase contact line where the liquid droplet meets the surface, solid surface, in the air medium or whatever in the gaseous medium. So when you are introducing the motion on the surface, eventually the tracking this triple phase contact, accurately tracking this triple phase contact line becomes very important. And for that we need to incorporate the kind of uh, we need to couple actually some other complex model. Okay, you cannot handle the things similar which are similar to the fixed surface. Okay, so in many aspects, this problem are complex and useful. So all the previous studies are mostly experimental and reported at a higher Weber number, let's say above 100. But in present study, we numerically investigated the droplet dynamics at the planes at different inclination angles in a wide range of Weber number, varies between 0.01 to 200. The effect of inclination angle on the droplet dynamics has been systematically studied. Here the range has been considered for 5 degrees to 80 degrees, and the effect of static contact angle on the droplet dynamics has been systematically studied. The range of static contact angle varies between 75 degree to 156 degree. It means that so if for a particular liquid uh, for a particular liquid droplet and a particular surface, they are having a constant SCA, static contact angle. Let's say you are using the water droplet and you are using some glass surface, so eventually the static contact angle will be fixed. Let's say it is 105 degree or whatever. uh, if you change the surface, in place of glass, if you are using copper surface, okay, or some other surface, eventually that static contact angle will change. So this is the significance. So if you want to change the material, you can change the static contact angle eventually. So the effect of the effect of the droplet shape, that is the spherical or non-spherical, uh, on the dynamics upon impacting the oblique surface over a wide range of Weber number, Reynolds number, inclination angles are investigated. So the non-spherical droplets are having special significance. I'm telling you why. Because if the droplet is small, eventually the gravity effect can be neglected. Small means we have found experimentally that if the droplet diameter, let's say, is less than uh, uh, 2.9 or 3 mm, eventually the gravity effect is not so much. That means the bond number is very, very less than 1. So you can neglect the gravity effect and eventually the surface tension retain its sphericity. But if the droplet size is more, let's say it is 3 or 3.5 or 4 mm, eventually you will see that when the droplet hits the surface, eventually it is not spherical, it becomes non-spherical. And this is the one thing. And second thing, if the surface is having the charges, okay, the surface content charges, eventually uh, uh, and you are putting some ionic liquids, a liquid droplet, eventually droplet becomes non-spherical. And another thing is, if you are using some polymeric droplet, so sometimes when it hits, it's stretched, okay. And another thing is that, let's say you are having two consecutive surfaces, like extends like this high power lines in the high power lines, okay, transmission lines. So um, if a droplet hits the first line, and then when it is going to hit the second line, its shape is deformed and it is no longer spherical. So you need to allow the droplet for certain time to retain its shape. So many times this hitting time scale is much lesser than the time scale required to regain its shape. Eventually at that point of time, these droplets becomes non-spherical, okay. And this issue has been rarely addressed in the literature, so we did it here. So the tangential and the lateral spreading factors, contact time, sliding length, and leading edge and trailing edge length, regime plots of the different dynamics, time evolution of the pressure velocity contour during the different dynamics over a wide variety of parameters, like Weber number, inflation angle, static contact angle, droplet shapes we have studied. And then the different we have, as I said in my earlier slides, that we have incorporated the different machine learning models, but here I will show only one, because yeah, it is a all together different domain of studies, so you can do lots of stuff. So yeah, here I must mention the challenges in the modeling. So due to the rapid deformation on the droplet free surface, it is extremely challenging to capture those multi-scale physics. Okay, hence very fine mesh is usually required. But sometimes we have seen that if your mesh size and uh, your grid size and a number of grids is not adequate, means you are if you are not uh, if you could not able to resolve the grids where the rapid deformation is happening, eventually that changes your dynamics. Means, let's say actual dynamics is rebounding, the droplet is hitting just like a ping pong ball, and it should rebound from the surface. But if the grid convergence is not properly done, eventually you will see the splashing. Okay, so you don't know. So if you don't have any reference, you don't know eventually whether actually it is the grid converged or not. So anyway, and again, modeling the triple phase contact line, there are different algorithms to model the triple phase contact line. So that is another important task. If you cannot able to track this triple phase contact line, eventually all of your calculation will be erroneous. So you need to be very careful about that. Then the dynamics of the droplet is a complex phenomena, and which depends upon the many forces acting on the droplet gas interfaces, droplet solid surface interfaces, and moreover boundary conditions plays a very vital role in this. As you know, in the CFD simulations, these boundary conditions are the game changer. So in case of either of the conditions is not properly maintained, the dynamics will eventually change. Now the modeling of, as I mentioned, the triple phase contact line is challenging task to implement. most of the literature reported the simulation using static contact angle modeling approach. Uh, uh, there are certain literatures they use the dynamic contact angle modeling, and for dynamic contact angle modeling means when the droplet is spreading or it is receding and whatever, at each and every time instances the contact angle is changing, right? Because it is a fluid. So there are different models like chrysalis model and other models for the dynamic contact angle, so you need to handle this differently. So results start to deviate from the actual one at the higher impact velocity cases where the droplet interface rapidly deforms if you are using the static contact angle models. So that's why the dynamic contact angle modeling is required. So due to the larger uncertainty in the behavior in the post-impact dynamics of the droplet, there are scarcity of the literature in the machine learning models also, as I mentioned earlier. Now coming to the computational domain. So as you can see, yeah, this is our computational domain. So in x, y, and z axis, it is the box, the size of the box, the simulation box is 30 mm cross 5 mm cross 6 mm. Eventually, the diameter of the spreading, the spherical droplet is 2 mm. Okay. So impact velocity, initial impact velocity is 1.5 meter per second. Angle of inclination is 80 degree. The droplet primary phase is water and the secondary phase is air. The wall bounded the wall boundary condition are used at the surface and the wall of the domain. So now once you made the simulation, so we have used the chrysalis model for the dynamic contact angle modeling that I did not mention explicitly. Then once the simulations are done, you need to what we did, we did the animation, and then we uh, 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 did the image processing. So these are the different stage of the image processing. From the animation, you need to convert the from the video to uh, the image frames, and from the RGB image you need to convert to the gray image, and then to the binary image with suitable intensity thresholding. And for that, if you if you want to do that uh, 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 automatically, mostly people use Ostrow's algorithm, and sometimes that algorithm doesn't work well, so we need to do it manually, and for that we need to check the image processing uncertainty also. And what we usually track the extreme points of the droplet where it meets the solid surface. Okay, so eventually you can calculate the axial spreading and the lateral spreading. Okay, you can calculate the depression of the vertex point of the droplet also, and that shows how yeah, how it height also varies. So eventually, if you can you can able to calculate the spreading diameter, eventually that is proportional, inversely proportional to the height of the droplet, because anyways it need to satisfy the conservation of mass. Okay, so yeah, so this is the machine learning algorithm. So we use several things: the decision tree, AdaBoost, uh, uh, and the SVM, supporting vector machines, and uh, uh, and other. There are lots of algorithms. There is a detailed study. So once the paper is under review, so I cannot reveal much. So once that is come, you can go through it. So anyways, so here my intention was to show how this algorithm works. Okay, so that's why I have included only one AdaBoost algorithm, so you can see the flowchart of this algorithm. That is, first you start, and then you give your input parameters. Okay, so here your input parameters are and y is the corresponding level. So your input parameters are, let's say, inclination angle, impact velocity, Weber number, Reynolds number, etc., what I have listed. And then you initialize the weights, as you know. you need to give some initial weight, and then the sample data set according to the weight gives the data set in the decision stamp. So the decision stamp will give you the prediction uh, uh, as yeah, here we have taken the parameter as age fx. Okay, and uh, then if your t is less than capital T, then compute the weight at uh, the next interactions, and eventually you will get the diameter and you compare it. If it matches, then yeah, the loop will go on, and if it doesn't matches, so you just calculate these parameters and the predict level for the xis, and then it ends. So yeah, and during the simulation, so this slide should come before the CFD simulations. If you see the model parameters, we have used the VOF, that is the volume of fluid method. The primary phase is water, the secondary phase is air, and the viscous model is laminar. Pressure velocity coupling, we have used the simple. The pressure discretization is presto, and the surface reconstructions is georeconstruct. The time step is 10 to the power minus 4 seconds, and the total number of time step is 150 to 400 depending upon the problems. If the impact velocity is higher, eventually you need more time step to converge, and if it is yeah, if the impact velocity is less, eventually yeah, your number of times should be less. So the physical time scale we have simulated up to 15 milliseconds. So why it is that? So within 15 milliseconds we have observed we can accommodate all the dynamics, and we have varied the static contact angle between 45 degree to 156 degree. Now, there are certain assumptions in the simulations that there is no heat transfer into the system. That is the isothermal assumptions. The droplet volume is constant. Viscosity of the liquid, and the liquid is incompressible, and outer air is compressible. So yeah, eventually you can see this is the overall geometry. So sorry, overall dynamics, what is happening, the leading and trailing edge length, why are they important, and how to calculate. So as I already mentioned that we have used 0.12 mesh size was found to be optimum for 12 black grid elements, and the simple scheme is used over piezo due to the simplicity and the computationally less expensive. And yeah, so the first one is the side view, and the and top view is also shown. So as I said, there are two different diameters. One is the tangential, one is the lateral. So tangential means along the axis. That is also called the axial diameter, axial spreading parameter, and the another one is the lateral one. So yeah, so these are, you can see the comparison of schemes and the grid convergence. So yeah, the first one is the grid convergence. So you can see once we finalize the simple over piezo, we run the different the simulation, the same simulations with different grid size, and we compared with the Guan et al. That is published in Causeway, and you can see the grid convergence. We have calculated the length is this is the sliding length of the droplet, and if you see the comparison of schemes, so there is as such no significant difference between simple and piezo. So simple is much simpler, that's why we use the simple. Yeah, so now these are the quality validation plots. Okay, yeah, so these are the validation plots. As you can see, the the first one, yeah, the first one is from Guan et al. Based on what we did all the validations, and the next one is the experiment. The first one is the simulations, the VOF simulations. The next one is the experiments by Sikalo et al. And the third one is Sahu et al. For the we have used this is the for the experimental validation. So anyways, so coming to the first figure, probably yeah, yeah, so this is the one et al, this is the Sikalo et al, and this is the our simulations at different the time stamping. Okay, so yeah, And yeah, this is for the inclination angle 80 degree. These are the visualization images and for these specific parameters, and these are the experimental validation with Sahu et al. And we have calculated the error that is always less than 5%. Now, yeah, now what we are calculating? We are calculating the spreading parameter, that is the instantaneous diameter. Because every time when it is spreading or whatever, so every time you can see that the diameter is changing, and we are non-dimensionalizing that using the initial diameter. So eventually, it is the ratio between the instantaneous diameter to the initial diameter. So that is called the spreading parameter. So yeah, so these are a few animations you can see for different Weber numbers at different inclination angles. So this is the your alpha at 30 degree. That is the inclination angle 30 degree. You can see, yeah, when okay. Okay. So when the Weber number is less, eventually I don't know what is happening. Um, yeah, when the Weber number is less, eventually you can see the depositions is there at 0.05. So droplet is not coming out of the is not rebounding from the surface. It is a pure case of deposition. So this deposition is very important in the spray coating, tablet coating, 3D printing, etc., where it is undesirable to uh, if the rebound or the splashing occurs. So when we increase the Weber number to 40, eventually you can see the rebound. This rebound is mostly applicable for the heat transfer applications. Okay, where the droplet will come, it will spread, and during that it will take the heat and it will rebound. Okay, so cooling, mostly the heat transfer and cooling applications. So when for the splashing, they are having different applications. So if we increase the Weber number to 80 or 150, you can see the violent splashing is occur. And even for depending upon the Weber number, the splashings are not equal. So different kind of splashings also can be observed. Okay, so now we increase the angle. You can see the 45 degree. Eventually, the dynamics changes, and now we are increasing to 60 degree for different Weber number. Now you see initially at Weber number 80, the droplet at 30 degree angle, the droplet was splashing. Now it is not splashing. We'll come into the details why it is happening, but mostly if you increase the angle, eventually your mg sin theta component, that is which is giving you the extra tangential momentum to the droplet, eventually that force is somehow uh, adjusting the effect of the impact velocity or the impact momentum, and it will taking away some impact momentum eventually. uh, uh, so the extra force that causes the splashing eventually is getting reduced, and the dynamics flip from the splashing to the rebound. Okay, so these are the quantitative measurements. So for different Weber number, different angles, you can see, and we have derived a correlation for these maximum spreading parameters in terms of Weber number and the inclination angle. So yeah, so as you can see, if the Weber number is increasing, eventually it is positively the Weber number is in positive power. So if you increase the Weber number, so the spreading will increase. But if you are increasing the inclination, if you are increasing the inclination angle, okay, uh, uh, yeah, so the spreading will decrease. Yeah. So now we have calculated the different the lengths, the leading edge and trailing edge length uh, for different inclination angle and for the different Weber numbers also. Okay, so yeah, so as you can see, as the inclination angle increases, the gravity component increases. As I said, the mg sine theta component, and most of the fluid volume accumulates on the leading edge of the droplet, and hence the leading edge length increases. For the similar reason, trailing edge length also follows the same trend. For a particular inclination angle, if you increase the Weber number, that means the impact velocity, the inertia component along the plane also increases, and hence the leading and trailing both lengths increases. Now coming to the regime plot. So this is very important. So we have characterized the different regimes based on the alpha and Weber number. So here we have listed only three regimes, that is the depositions, rebound, and splash. Okay, yeah. So now these are the effect of different SCO static contact angles. Okay, and for different Weber number, as you can see, the dynamics is changing when you are changing the static contact angle or the materials, and we carried out the similar kind of studies. I'm not going into the details, but here as just I want to mention one thing. So below 90, if the static contact angle below 90 degree, that means the surface is hydrophilic surface, and if you increase from 90 to 120 degree, it becomes the hydrophobic, and more than 120 degree, it becomes the super hydrophobic surface. So eventually, if your surface is hydrophilic, eventually the droplet spreading will be more, and more the surface is becoming the hydrophobic, your the spreading will start to decrease. Okay, so yeah, we performed for different materials, for different angle of inclination, for different Weber number. Okay, so yeah, so as you can see at angle 30 degree here, there is an important observation that at 30 degree angle, if you run the simulations for Weber number 40, eventually you will see after reaching the maximum spreading, the droplet is splitting up. We are not saying it is very different from splashing. So in splashing, you cannot able to calculate the spreading parameter at all, but here the droplet splitting is taking place, that just the droplet is reaching its maximum, and when it start to recede, eventually it splitted up into the pieces. So that is called the droplet splitting. Okay, yeah, so okay, now this is the results obtained by the AdaBoost algorithm. That is, from this table you can see we have calculated these parameters. These are the accuracy, precision, recall, or sensitivity, F1 score, and mean square error. Okay, so yeah, so yeah, and this is the true table. Okay, and that is the TP stands for true positive, FP stands for the false negative, and TN. Okay, so these are the things, these are the self-explanatory. So what is happening? So yeah, in this table, let's say uh, what is happening actually, it is in your in your y-axis, and what our model is predicting, that is in your x-axis. So as you can see, in the deposition case, if you see the first row, so mostly for the 12 models, it is giving it is predicting exactly deposition, but for two cases, actual is deposition, but our model is predicting the rebound. And for the rebound cases, yeah, so for 15 models, our for the 15 cases, the model exactly matches, but for one cases, actual is rebound, but our model is predicting deposition, this one. And for splash also, you can see it exactly matches for 12 cases, but in one cases our model says rebound, but that was actually splash. So in this way you can check the accuracy of your machine learning models. For different models these numbers will change, this number will be different. Now coming to the conclusion, at lower inclination angle, at lower inclination angle the Weber number uh, the lower SCA, the results in a greater spreading factor due to the hydrophilic nature of the surface, as we already mentioned. And as the SCA increases beyond 90 degrees, the surface becomes progressively more hydrophobic, and beyond 120 degrees, it turns to be super hydrophobic, leading to decrease in the spreading factor. At a higher Weber number, the partial splashing was observed, that we are saying the droplet splitting across all SCs up to the inclination angle of 30 degree. When the inclination angle reaches 45 degrees, the droplet dynamic shifts from the splashing to rebound due to the increased axial momentum transfer caused by the higher inclination. And a classification-based machine learning algorithm, AdaBoost, was developed to predict the droplet dynamics based on the CFD simulation results. This algorithm achieved up to 90% accuracy in predicting the droplet behavior on inclined surface, with potential uh, 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 for improved accuracy for the larger data set. Now coming to the case study 2, that is the numerical simulation of post-impact dynamics on a droplet on a moving surface. So so previously we discussed in brief that up to the author's knowledge there are very few literature available on the droplet impingement on a moving plane, and most of the studies are experimental in nature, where there is a scarcity in the numerical studies. So there is no comprehensive study available which explains the effect of impact velocity on the droplet, tangential velocity of the plane, surface wettability, and the droplet size altogether. So most of the studies discuss the spreading in axial directions, while the spreading in transverse directions or the lateral direction during the post impact is also important to consider. So in the present study, what we did, the effect of normal impact velocity of the droplet upon impacting a moving plane is numerically studied. The effect of surface wettability, that means the effect of different static contact angles on the droplet dynamics upon impacting the moving plane is numerically investigated. The effect of tangential velocity of the plane, okay, on the its post-impact dynamics has been studied, and the effect of the size of the droplets, hence the effect of gravity on the post-impact dynamics, were studied in a wide range. So this is now uh, uh, the simulation geometry and the simulation geometry and the uh, boundary conditions. Okay, so this plate is moving. So again, for the simulation setup and the simulation assumptions, as you can see, this case is happening like this, and you see the altogether it is a different dynamics. So here we have used these parameters I have listed here, and we have conducted the validation study, and you can see the validation error. The error in calculating the spreading factor is 4.5 to 5% around, and which is in the permissible range. And from the visualization experiments from Zhang et al, you can see our simulations are in agreement, in a good in agreement with their experiments. Okay, yeah. So now you can see, um, yeah. So first consider, we are keeping constant. If you see the first row, this first row, we are keeping the tangential velocity constant. That means the tangential Weber number, and we are varying the impact Weber number, or the impact velocity, or the normal velocity of the droplet. So eventually you can see at Weber number 40, you can see the splashing. But when we are increasing now from here to here, when we are increasing the tangential velocity from 0.5 meter per second to 1.5 meter per second, but keeping all the normal velocity or the impact velocity same, you can see at the Weber number 40, it is no longer splashing. The dynamics become changed from splashing to rebound. This is because of this tangential motion of the plane is imparting a tangential momentum to the droplet, and that is somehow uh, adjusting the impact momentum that causes the droplet to splash. Okay, and these are the quantitative visualization of the data, as you can see. Okay. Yeah, so when we are increasing the impact, as I said, for the lower tangential velocity of the plane, if we are increasing the impact velocity, eventually the droplet start to splash after reaching its maximum spreads. Uh, but when we are increasing the surface velocity of the plate, eventually you see now the droplet is not splitting or not splashing. Okay. Yeah. So yeah, here we have changed the different we have changed the surface, impacting surface. So that is why the surface contact angle is sorry, static contact angle is varying. All of those results are reported for 0.5 meter per second tangential velocity of the surface, and and for particularly yeah, so previously it was for impact velocity at impact Weber number at 10, and now it is at impact Weber number of 40. As you can see, at the lower tangential velocity of the surface, eventually the droplet splits up after reaching the maximum. But eventually, at any Weber number, the droplet doesn't show the splashing when the tangential velocity is more. Okay, that is yeah. Now coming to the variation of bond number. So that is what I wanted to discuss, that if your droplet is not spherical, means if your droplet size is larger, eventually your bond number will be larger. So at certain point of time, you cannot neglect the effect of gravity. Eventually the gravity effects come into the picture, and so that is what, if you increase the bond number, yeah, you can see the expression of the bond number here. So yeah, it is the effect of gravity to the surface tension. So if your gravity effect is more, you cannot neglect the bond number. So eventually the gravity plays a role in the post-impact dynamics of the droplet, and that you can see for different tangential velocity and different impact velocity also. Yeah. Okay, so I'm not going into the details. So just coming to concluding for the second case study, that at a lower impacting velocity and at a lower translational velocity of the plane, yeah, rebound of the droplet was observed at the same lower translational velocity of the plane. As the impact velocity increases to 40, the partial splashing or splitting was observed. Uh, so as the translational velocity of the plane increases, the spreading time of the droplet increases due to the extra, as I said, the extra axial momentum transfer to the droplet at a lower impact velocity. And interestingly, at a higher plate velocity, the droplet with the higher impact velocity, higher plate velocity, the droplet with the higher impact velocity doesn't break due to the suppression of the normal momentum that causes the splashing, basically by the transfer of excessive axial momentum to the droplet by the plate. At a lower SCA, the spreading of the droplet is more due to the hydrophilicity of the surface, and subsequently decreases in the increase in SCA. That means the hydrophobicity increases at the lower Weber number. However, at the higher Weber number, droplet breaks up from SCA of 135 degree onwards. As the size of the droplet is getting lesser, that means the lower bond number, the gravity acting on it is also less, and that decreases the horizontal or the tangential momentum imparting imparted to the droplet, which eventually reduce the spreading and the contact time. However, as the tangential velocity of the plane increases, the additional tangential momentum is transferred to the smaller droplets, which adjust the tangential momentum deficit due to the lower gravity effect, and this eventually causes the increase in contact time of the smaller droplet. Now coming to the last case study that I will touch upon, that is, so apart from, okay, I will take another 5 minutes. So yeah, so this is our, so the previous two case studies were hardcore CFD and some sort of based on those data, some sort of machine learning. And you know those VO based simulations are the grid based techniques, okay, and it depends largely, the dynamics depends on the boundary conditions, grids, etc. Now here we are showing the a similar case studies, that is the atomistic simulation of post impact dynamics of a droplet on a moving plane. So yeah, so as you can see, the plane is moving and here the droplet is impacting on it and in the nanoscale level, and the size of this droplet is around 10 nanometers. This is the nano droplet, and as you know, if you go below the micro level, that means 10 to the power minus 6 meter, right? So millimeter, micrometer. So if you go below micrometer, eventually the continuum hypothesis fails. So you cannot simulate the things based on the traditional uh, moment Navier-Stokes equations, based on the traditional momentum based approach, or whatever Newtonian mechanics. So for them, we need to do um, uh, the atomistic simulations or the classical molecular dynamic simulations for the, and at that scale, this nanoscale level, eventually the interaction between the molecules themselves, interaction between the molecules and the surface becomes very important. And for them there are lots of other models available. So here we have used TIP4P water model. For that, the Coulombic attraction parameters were listed down. So these are not so straightforward, you need to study it. It is very different from CFD, and we did it for different validation cases, okay. So you can see these are the range of our present uh, uh, the present range, that is the tangential Weber number is from 100 to 300 300 tangential Weber number at a particular impacting Weber number of 15, okay. And for the validation purpose, we kept this at 7.41, this impacting Weber number. And so here you need to, during the simulations, you need to list down all the energy parameters, interaction parameters, or the energy parameters that are available in the literature for a particular model, okay. And we have varied the different speeds, the tangential velocity, okay, and we calculated the spreading parameter in x direction and the maximum spreading parameter in x direction and maximum spreading parameter in y directions. And we observed something interesting, that is the some hole formation or the gap formation occurs while the droplet is spreading in certain cases. And yeah, so we listed down those time step gaps and the contact time. Yeah, as you can see, so basically these are the particle based methods, and here we have taken the 5,000 particles, and every time, depending on the energy state, these particles are just leaving the surface because of the energy mismatch, and that is very common in the molecular dynamic simulations. So this is the validation. So as you know, in this scale, normally experiments are not available, okay. So sometimes people validate these molecular level experiments with molecular level simulations with experiments uh, by incorporating some correction factors, okay. So here we have validated our model with the Zhang et al. 2022 model, and you can see our results are in good in agreement with them. And then we performed the similar studies, that is the that what we did for the CFD, that is the droplet impingement on the moving surface. Eventually, you can see this is the beta x, that is your axial spreading parameter, and this is your the lateral spreading parameter over different different tangential velocities. And here we have kept the impacting Weber number at um, uh, probably 15. Okay, we are not changing the impacting Weber number, rather we are changing the surface velocity, and we got this kind of dynamics. So here I have not listed the conclusion because the study is ongoing. So it is not good to show wrong results. But I wanted to give an overall view. That's why I have included this. Apart from CFD, in the industry, we also do these molecular level simulations, because these are important mainly in the semiconductor processing industries, or where we need to see what is going on at the molecular level. And mostly in the computational material science, these kind of studies are very important to see how a particular type of droplet is interacting with a particular surface of particular surface, kind of, if this water droplet is impacting on the graphene surface, or it is impacting on the copper surface, or it is impacting on the aluminum surface, whatever, the surface interaction parameters will change, and eventually that will change your dynamics, and eventually your outcome will change. And sometimes it is very important to see the corrosion in the materials. So for those kind of studies, this molecular dynamics is very useful. So thank you. I think I have completed with it within time.
Yes, sir. Thank you.
Yeah.
Over to you, Payal ma'am.
Hello.
Yes, sir.
Any question?
If any participant is having questions to Mr. Arnab sir, you can ask him in the chat box or unmute yourself as well.
So there are some questions in the chat box.
Okay, I can see only one question. So, yeah. So, what is the question? Can you please tell which solver was? Yeah. So, solver is already mentioned in the PPT. Just a minute. Yeah. Oh, how do you decide which solver to use, simple or piezo? Yeah. So, you cannot decide based on that. So, okay. We conducted some cases. Oh, we conducted, you need to conduct some cases and see which solver is giving you what kind of results. So as you can see here, so yeah, run the same simulation using piezo and simple, and you see what is the difference in error, and compare that with your some standard cases that people have already reported. And if you see the error is less, like is insignificant, then yeah, the simple is more convenient to use than piezo due to the convergent issues and all.
Hello.
Yes, hello.
Hello, yes, sir. My question is that how you select the appropriate data set for their machine learning model, and what are the
Data set.
criteria you have selected for this data set is perfect for this, or while performing this machine learning model to integrate that?
Yeah, data set, see, for machine learning model, as you know, so we are having some plan to do pins also. So the thing is, for these machine learning models, you know, you need to have a larger data set, right? So first we conducted all the CFD simulations. Let's say lots of CFD simulations. Here I have shown you very specific cases. So once you acquire the data, then only you can do machine learning. Otherwise, there is no point in doing machine learning, right? Because you need to train your model. For that, you need to spend 20% of the data. Let's say we used 2080 kind of thing. So you need to train your model for the 20% of data, and then you need to predict it. So eventually you need to have a very high volume of data set, whether it is experimental, whether it is simulations. But yeah, first you need to conduct the simulations. Otherwise you cannot do the machine learning.
Sure.
Yes, that answers your question.
Yes, yes. And second, my question is that by selecting the data set, you have to be selected the simulation time steps. So some information in between is lost if you're taking the larger time step simulation data to tuning the machine learning models. So how you decided that this data sets and data
See,
time
first
steps?
you forget about the machine learning. First, as you know, for the CFD, we usually do two kind of grid convergence. One is the mesh, the spatial convergence, and one is the temporal convergence, right?
Yes, sir, yes.
Yes. So first you focus on the CFD simulation. So you do whatever is required for the CFD, and once the data is accurate, because if you cannot, you are talking about the time step. That's why I'm telling. If you are if your times the if your simulations are not converged in temporally, what will happen? Let's say actual dynamics is something at let's say t is equal to 1 second, but your model is giving something else in the t is equal to 1 second. So first focus on the CFD simulations, the grid, the spatial and the temporal grid resolutions, and once it is done, then you use those parameters in the machine learning model. Otherwise it won't able to predict, or in fact after that we used to reconstruct the surfaces, right? So we want to um, build the similar kind of dynamics, similar kind of images. Those we usually get from the CFD. So you are getting my point. So let's say at certain Weber number you don't have CFD data, but you want to reconstruct the surface. How can you reconstruct? So based on those data, so those data should be accurate. So yeah. So to answering your question, so
Yes, sir. My question is that if your simulation part is accurately, you have validated and you have to done grid independent based studies, these are correct. Then after you have to make decision that how much appropriate data you have to tune data set in terms of their image.
So there are, yeah, so as you can see there are if you see the literature, so sometimes people tune 25 train the 25% of data set, right, and then predict. Sometimes 20%, it's up to you. So we have used 80-20 model.
Okay. Okay.
Okay. Now what is the case? First case mention application with deposition and rebound dynamics can be, you can elaborate on the applications where splashing dynamics can be utilized. Yeah. So yeah. So the splashing, see, splashing is having many applications. Like, yeah. So in nature, if you see um, this disease spreading. So if your impact velocity is very high, eventually for the rebound and etc., you can see it will go deposition. The spreading is very less. If you see the rebound, so in that case also it will go up to certain uh, uh, it will go up to the certain length, and then it will start to recede. But if it is splashing, eventually the droplet, the part of the droplet volume or the droplet mass can spread here and there, and eventually the risk is more. Okay, this is the one thing. And another splashing application in the nuclear power industry, let's say. And in nuclear power, what happens is sodium droplets. So for the if you there is certain leak, and eventually the cooling water or the reactive water usually comes, and uh, it hits the some cylindrical pipe surface, right? And it splash because those pipes are hot. So yeah, so depending upon the intensity of splash, uh, it severely affects the heat transfer characteristics as well as uh, creating local cooling. So you know the materials, if suddenly cooling and heating takes place, eventually that affects the material, right? Yeah, and that, and there are other effects also. Uh, so um uh, if you see exclusively this splashing, um, yeah, so for the timing I can remember only these two applications, because mostly uh, my cases generally we focus on the deposition and rebound, and we try to look into the limits where the splash starts. Okay, so that we can avoid it. So yeah, so what I can remember, I can say as of now these two applications. So that answered your questions, I think, Soham. And next, how the bond number significant for the bubble flow. Okay, so as you know, the bubble rise. So I do not work on the bubble flow, so I cannot say it explicitly. I cannot comment on it because it will be wrong if I comment uh, without knowing it. But what I know, what I have seen from simulation, so bubbles rise on the just opposite to the gravity, right? And droplet is always coming due to the gravity. So eventually my assumption is that eventually the dynamics will be the opposite. So for us, we neglect the bond number. For bubble, we cannot neglect the bond number because eventually it is going against the gravity. So it should be it should be simulated in a high bond number. And for bubbly flow, yes, the bond number is every time important, because as you can see that bubbles always grow against the gravity, right? I hope that answer your questions. And what are the experiments and experimental setup? No, we did simulation. We have not done any experiments. So which solver can we simulate? Moving particle. So there are so yeah. So for the moving, no, you were saying about moving particle or moving contact line. So for moving particle, uh, if you're saying the droplet is impacting, no, that can be done in the normal solver. But if you're asking for the moving contact line, then yes, you need to write UDF. So there are lots of models, the Chrysler models and other Zhang models. So there are lots of models nowadays available for the interface tracking. So you need to incorporate them in a separate UDF and patch them up. So you have done the phase change simulation in upload a format. No, no. We so if you see my assumption slide, I have explicitly mentioned that there is no heat transfer. So we are having a plan of doing it in future, because our applications were mostly on the tablet coding, 3D printing, those kind of stuff. So there, the heat transfer was insignificant. What are the most significant open challenges understanding multiple flow and tablet in the conveyor still struggle with? Yeah, triple phase contact line. But because if it is an evaporation case or condensation case, or the surface is moving, if the surface is even rotating, every time that the behavior changes. So the DCA models, dynamic contact angle models, that is a big challenge. And can we verify this? Yes. So many people did experiments. So you can see sometimes we verified with Sao et al. Professor Purbanandha's group at that point of time. It was in IIT Ropar and now it is in IIT Kharagpur. So they did extensive experiments. So yes, those results can be verified using experiments. But for us, we did not have the experimental facility, so we need to rely on the literature, the what other people did experimentally, and that is what the simulation guys do. If a droplet is formed in a supersonic gas flow, very good question. The pressure and temperature drop with multi-phase solver model. I don't know. I need to check it because I have seen this kind of experiments in my present lab, that droplet shock interactions. Yeah, uh, is very similar to your question. But in simulation, I need to check for which kind of model we can use. So I hope we have answered all questions.
Hello.
Yes.
Yes, sir. Sir, my question is your last part of study, which you have done nanoscales bubble formation.
Yes, those simulations are still going on. Please ask. Yeah, you can ask.
Yes, sir. You have to consider the particle-based model for that formation of bubbles. During this, you have to be consider some forces and particle restitution coefficient and particle interaction is taking place.
Yes.
How you taken that parameter? How these are
Oh,
very
those, yeah, that is a very important question. The thing is, for the at least we have started this kind of simulations.
yes, sir.
So what I can say is, yeah, it is very difficult to simulate for the unknown things. So we started for uh, those kind of liquid and surface. Those the datas are available in the literature, in the previous literature. So later we will think how to simulate the unknown things, but as of now, I don't have much idea on that.
Okay, sure.
Yeah. We stay in touch. Probably in the next session, whenever I'll give a talk, I can make an explicit and exclusive presentation on this. Okay.
Yes,
Yeah, because unless you are studying the things very rigorously or in a detail, it is not good to uh, mm, answer based on your assumptions, right? Yeah. Any further questions?
no, sir, no, sir.
Hello, Payal.
Yes. I can see that, I think all the questions you have answered on the chat box also, and those who have asked through your audio also. So thanks a lot. Thanks a lot, Mr. Arnav. So you have been very patient in, answering all the questions. And, your presentation was also so informative. It was so detailed. I hope all the
Thank-
participants have been, it has been very effective for all the participants. Yes, thank you. So, Mr. Arnab Chakraborty was a member of the advisory board of the CFD team of FOSSI, and sorry for the. Yes, so I was saying that Mr. Arnab Chakraborty is one of the esteemed member of the advisory board of the CFD team of FOSSI, and he is from TCS Research and Innovation, TCS Innovation Lab. And it has been very, he has been very generous, and we are very thankful to him for this session. So thanks a lot. Thanks a lot, Mr. Arnab.
No problem. Thank you.
Thanks. So we will move ahead with the demonstration session next. So Nikhil, have you joined? Yes, I can
Yes,
share. I
ma'am.
can see Nikhil. Yeah, thank you. Thank you so much. So we can start the demonstration session, or if the participants need 1 or 2 minutes break, we can do that. Otherwise, we can
Uh,
directly start.
Okay, ma'am. Fine.
Yeah.
So we
Okay,
can
so
start the
you
session.
can start. Yes, yes, you can start.
Okay, okay, ma'am. Yeah.
So I would request
So,
all the participants to note down your questions. You can also type in the chat box. Also, you can note down in your in your personal notebook. And after Nikhil's session, you can he can take all the questions. Our team members are there; they can all take your questions. Okay, fine. Over to you, Nikhil.
yes, ma'am. Yeah. So, based on this Arnab sir session, I will going to demonstrate some few of the cases, which is also based on a droplet and bubble. So let me share my screen. Uh, Screen is visible, ma'am, or?
Yes, sir.
Oh, okay, okay, fine. Yeah. So, we're going to see the same two-phase flow based on VOF method. But yesterday, what we have seen, it was based on two continuous fluid interacting with each other, like a wave and dam break case. But in the today's case, uh, I will going to cover these two cases, which is bubble rising using VOF and the droplet case. So we'll see one by one all these two cases. So coming to this bubble rising case, so in this, uh, it is something like air is trapped inside the water column. So this is the geometry of that test case, and we will going to uh, trace the interface of the air bubble, which is trapped inside the continuous water phase using VF method, and we'll going to see both the cases with static mesh and with the dynamic mesh. That is the adaptive mesh refinement. So these are the again same governing equation which I have covered it yesterday. So again, as a recap, so the first one is the uh, continuity equation. Second equation is the momentum equation, in which gravity and surface tension term will act as a source term. And to capture the interface, a phase equation, uh, it will going to solve. So coming to these boundary conditions, so this is our geometry, and this three wall has been given the no slip boundary condition. That means the velocity on all these three wall is zero. And this is the pressure outlet condition. That means the atmospheric condition, which means the bubble will leave this flow domain from this patch. That we're going to see how it will going to leave. And on this bubble, the gravity and the buoyancy force will going to act. And because we are capturing the interface, so we can easily calculate the buoyancy force based on the deformity in the shape. So coming to the test case, so this kind of test case we can easily modify using the same dam break case. And so let me show you how to modify it. So other things will be same, like inside the zero folder, there will be three files, pressure, velocity, and alpha phase one. So if you see alpha phase one, yeah, yeah. So here we are defining on all the walls as zero gradient. That means with calculation, it will going to uh, calculate the value of alpha on these walls. And we are solving for the 2D case. That means front and back will be the empty. That means it will not going to solve for the front and back cases or patches. Similarly, coming to pressure and velocity. So as I have said that uh, no slip boundary condition has been implemented on the wall. So instead of so both the ways we can define no slip boundary condition. Either we can define the velocity, all three velocity as zero, or we can simply write as no slip. And again, the top patch has given the boundary condition of pressure inlet outlet velocity. Now, similar to velocity, pressure has given wherever the velocity is a fixed value, the pressure will be the zero gradient. So that's why on all the walls, zero gradient boundary condition is implemented for the pressure. Now, uh, the mesh will be the mesh will become the very simple. Using the block mesh will define the mesh, and it will be a simply a rectangular box. So that also I will show. Yeah. So it is simply a rectangular box. In these are the vertices mentioned here. And instead of dividing the whole geometry into various blocks, we can define it as a single box, single block, where the x, y is divided into these many subsections. So first we'll see the mesh, and then we'll see how to initialize it for the bubble case. So I will go to that location. I'm using OpenFOAM 2412 for running this demonstrative case. So first, I will make the mesh. Using block mesh command. Then we can check it using check mesh. So our total number of elements are 12,800. So if you want to visualize now, we'll simply open the para view to visualize our basic mesh. Yeah. So this is our computational domain. And if I select surface with edges, so you can see the mesh given for this computational domain, and it is very fine. So in case of this surface or interface capturing application, it is advised to give a very fine mesh to properly capture the interface. If you are not changing the mesh using adaptive mesh refinement or any other technique. So because our mesh is static, so everywhere we have defined this fine mesh. So now coming to the initialization. So again, the initialization will be done using set field dict. Yeah. So the default value, because it's air trapped inside the water column. So everywhere we'll first define the water as phase 1, means the alpha value of 1. And to define the bubble as initial condition, we'll define it something like this. We'll define it as the 3D cylinder. Anyhow, the front and back, it will not going to solve. So it will appear as a 2D circle. So we'll define the point that it means the center point of the circle in on both the planes and the radius. And based on these points and radius, we'll define our volume scalar field alpha value of 0. So alpha value of 0 will initialize the bubble. So we'll see. I should create new alpha file. Yeah. So using set field. Yeah. So now you can see it is saying that on these points with this radius, it has initialized alpha phase of 0. And if we'll see this alpha file also, we can compare both alpha original file and the initialized file. So in alpha phase 0, the internal field is showing the 0 value, means everywhere in the domain only air is or alpha field is there. But after initialization, it has initialized some values of 0 and 1. So wherever we have defined uh, the cylinder to cell value of 0, it will take 0 value there. Otherwise, everywhere inside the domain, it will take the alpha value of 1. So now if we initialize this, visualize this. Yeah. So we'll simply drop down this one and we'll click on alpha phase 1. So now we can see uh, blue patch is appearing here. So this blue patch is nothing but the alpha phase of 0, which we are referring it as the air bubble, and this red phase is the water column. So to see the uh, bubble rising dynamics, uh, I am using the solver called as Interform, which is well known for tracking the interfaces, which I have showed yesterday also. I will simply run this Interform solver. So as it is a 2D geometry only, it will not take much time to complete the simulation also. Till now, if you'll see, it has run till 0.82 second. And it has started saving the files also. So it's better to visualize. So we'll first refresh it so that all the time step will appear on the para view. So now if you'll see 111 time steps it is showing, which are appeared. So we'll simply switch on the play and we can see how the bubble is deforming inside the water column. So anyhow, this is taking time to show. So the animation I have made here. So you can visualize this, how the bubble will going to deform inside the water column and how it will going to leave the fluid domain from the top patch. Yeah. So in this you can easily track the interface of the bubble, and using Paravi or using some open form utility, you can also calculate the volume of the whole bubble. So this was the first case. So after this, if some questions are there, we can take, or ma'am, should we take questions now or towards the end?
Maybe we can take at the end of both.
Okay, fine.
Yes.
So similar to this rising bubble case, in the previous section, we have seen some droplet cases also, which Arnab sir has demonstrated. So we can simply reverse the initialization. We can see that. Yeah. So instead of giving the default value of 1, we can give the default value of 0 and initialize the droplet. Uh, so again, in the same set field, so earlier, if I'll compare the with the bubble rising case, here I have initialized the default value of alpha 1. That means everywhere it will take the alpha value of 1. Means for this case, we are considering it as water. Now, in case of droplet, when we want to see the droplet impact on the solid surface, that in that case, we'll initialize the default value as 0. Means everywhere it will take default value of 0. That means it will take it as a air domain. And to initialize the water column, water droplet, again we have to define the 2 points radius, and we'll initialize it with the alpha value of 1. Yeah. Remaining things will be the same. Means how we are giving the boundary condition for the bubble rising case, and the properties will be also same. Only now instead of bubble, we are considering it as a droplet. So I will simply change the folder. Yeah. Now this will also consist of the same block mesh. Check mesh and set fields. Yeah. So now you can see it has initialized the droplet at these two using these 2 points with radius of 0.25. Now, if we want to visualize this, so this is our fluid domain with the mesh refinement. And if you want to see the initialized field, then again we have to select this alpha. So now you can see this red zone is denoting the water droplet, and this is the air domain. So now if I will start solving this whole fluid domain, now because of the density and gravity, the heavier fluid will slowly come down and impact the bottom surface. So that we'll see. So again, as this is the interface tracking case, again we'll use the interform as a solver. And the properties of the fluid, it is nothing like it is defined alpha dot water, so you cannot vary the density of or kinematic viscosity. It depends on the application that or what kind of fluid you want to take. So as this is a 2D case, it will also not take much time to solve the whole fluid domain, and we can see the nice animation out of it. So by the time it is solving, this is the computational domain for the droplet case. Now, instead of buoyancy force, which I have showed earlier for the bubble rising case, now for the droplet case, the drag force will come into existence. And this also we can calculate as the bubble will come down, its shape will deform. And based on its shape, we can simply calculate the drag force. So this is how the bubble will fall and hit the bottom surface. We can stop in between and see if it is taking too much time. So we can simply select alpha water. So the animation that I showed was having some different viscosity and density. That also I can show what the velocity, sorry, not velocity, density and viscosity I have taken for solving this case. And in this case, which I am showing it right now, uh, here I have taken the density and viscosity of water and air. Yeah, so this is how it will going to impact and the splashing effect. Now, in the droplet case itself, if you want to simulate the hydrophobic or hydrophilic nature or as a property of the drop, so that also we can define. Yeah. So here I have defined the water phase as Newtonian with a kinematic viscosity and density, and air is also defined as Newtonian fluid with kinematic viscosity and density of this much. And this is the sigma value. So this also you can vary. So suppose instead of this, if I'll take these value, which is uh, the kinematic viscosity of 0.01, that means it is a too much viscous fluid. So we can see how it will going to affect the drop dynamics. And if we'll increase the sigma, that is the surface tension, so it is means compared to water, this the sigma is too high. So we can compare based on that. So I will delete this one. Yeah. So for this case, I have only changed the property of the fluid. So no need to initialize it again and again. Directly, I can use the interform command to simulate for this case. But whenever you are changing the mesh or geometry, or not geometry, only the mesh. So currently, I'm using the mesh size, total mesh element of 12,800. But if you are refining it further, after refinement of the mesh, again you have to do the uh, set fielding. You have to run the command of set field to initialize it again. So you can see we have simply changed the properties of the fluid, of both the fluids, and how it will going to behave, we can visualize from here. So earlier I have taken the properties of fluid of water and air. So now some random values I have taken. So now you can see while the drop coming down the whole domain, the shape is not varying that much. It is uniformly distributing in both the direction. So the animation of the same uh, simulation I have showed it in the slides. So I've stopped it in between. So that's why it has simulated till this point only. If you'll simulate it further for the time steps, you can see it will come down and hit the solid wall. Now both the cases which I've showed, that is the bubble rising and droplet case, here our mesh is not changing. And also to capture the interface, we are requiring this fine grid all over the domain, which is not required sometimes because we are only capturing the interface. But what about this portion? Here, this much refinement is not required, which will anyhow increasing the computational time. So to counter this, we can use adaptive mesh refinement. So what it will do, it we can make a very coarse grid, and it will only going to refine where we want to capture the interface. So that case also we'll see, and how it will speed up our simulation. So this is the bubble rising case with AMR. AMR is nothing but adaptive mesh refinement. So again, the boundary conditions and everything will be the same. What will going to change, that I will show. Now, in the constant folder, other than these three files, that is G, transport properties, and turbulence properties, one more file is appearing, that is dynamic mesh file. So whenever you want to do the dynamic meshing, dynamic mesh refinement, or adaptive mesh refinement, it will not you cannot use adaptive mesh refinement when you don't have any scalar properties or scalar as a variable, because if it want to trace or any interface or any other dynamics, it requires some scalar properties. But for this VOF method, we already have one scalar field, that is the alpha scalar field. So based on this field, uh, it will going to trace the interface, or it will going to refine the mesh. So in this dynamic mesh dict file, we'll first define what is our field. So we are giving the alpha field. Now we have to define up to what level it will going to refine. So the lower limit and upper limit we have to define. And in between this two limit, it will capture the interface of the either the droplet or the bubble. Now maximum cell we have to define, that this much cell is required to capture the whole interface. We can increase or decrease based on our requirement also. So after defining this, I can show the basic mesh, how coarse it is. So I will delete this file and I will make a new alpha file. So if I'll open it, you can see it is not initialized yet with an internal field of 0. So first we'll create the mesh. So now if I'll compare both the uh, refined means the earlier bubble rising block mesh dig file and this block mesh dig file, so you can clearly see how coarse uh, this block meshing I am giving. Yeah. So this was the earlier file where we are refining all over the domain. So in this, the x uh, length or the width, we are dividing it into 80 subdomains. Y we are dividing into 160 subparts. Now coming to the adaptive mesh refinement, I'm giving only 10 and 20 in x and y direction, keeping all the mesh elements as uniform. So now first we'll see our block mesh. So now compared to 12,000 cell in the fluid domain, now it is only 200 cell.
Nikhil, just let me interrupt once.
Yes, ma'am.
Actually, we have put the attendance sheet. Okay, the participants can take 1 minute break and they can just mark themselves present, and then we can continue again.
Okay, ma'am. So after 2 minutes, we can
Ah,
restart it.
yes, yes. I'll just copy paste the link once again here to the
Okay,
chat
ma'am.
box. Okay, I think some of them have already marked themselves present. Let us wait for 1 more minute and then we can start.
Okay, ma'am.
Nikhil sir,
Yeah.
in the meantime, can you tell me which tutorial have you used? Many of the candidates are asking for the tutorial case file.
Okay, okay, okay. Fine, fine, fine. It is, let me check.
Yes, sir. Or else we can share it up once we are taking question and answer.
Yeah,
As-
that will be fine. Yes.
Yes, okay.
I think we can continue.
Yes, ma'am.
Okay, ma'am.
Yeah.
Okay. Okay, fine. So I was showing the current block mesh with adaptive mesh refinement. So we can see earlier our mesh size was 12,800. Now it is only 200. So we can see how coarse it is. And we'll also visualize how the interface is coming after initialization. Yeah. So you can see compared to, it's better to open both. So this was the earlier mesh domain in which this much refinement we have given to capture the interface. But for the adaptive mesh refinement, this much coarse mesh we are giving. So the idea is we're not going to refine the whole domain. We're only going to refine the interface, which will help in speeding up the simulation also. And the maximum refinement near to the interface we are giving as 40,000 mesh total mesh. So now we'll go for initialization. So again, for the initialization, the same file I'm going to use. So it's a bubble rising case. So everywhere default value is 1. And only for initializing the bubble, I'm giving the alpha value of 0. So I will run this set field command. Yeah. So now it has successfully initialized. Now if we'll visualize, now if we can see how means it's just an initialization. So how badly it has captured the bubble. So it is because we are not giving that much refinement to resolve the interface. So now coming to solving this using adaptive mesh refinement. So the adaptive mesh dynamic mesh dig file I have already shown that how it will going to resolve the interface based on this upper and lower limit and the maximum cell size of 40,000 we are giving to capture the interface. So now if I'll run the interform, we can see with each iteration it is showing that how much cell it has refined. Yeah. So after the time step of nearly 0.6 second, it has refined almost 2000 cells. And as the time approaches, it will keep on showing that how much cell it is refining. So it has already reached the time step of 1.5 second. So we'll stop in between and we'll visualize it. So now you can see as the time with time, how it is nicely capturing the interface and the same what we have seen earlier, how the bubble will behave inside the fluid domain. The same behavior we can see it here with the coarse mesh with adaptive mesh refinement. And to further refinement, you can increase the maximum cell size and the upper and lower limit. So now you can see compared to the initialization, how well it is capturing the interface. Anyhow, it will take much more time to escape this fluid domain. So it's better to stop, and I will show how it is refining the mesh. It's better to switch this on. Yeah. So now you can, it's better to switch off. So the mesh visualization will be easy. So now, if you'll see how the mesh will start to refine near to the interface, and slowly it will going to change. So because of this, means the whole domain is having very coarse mesh. Only it is refining near to the interface of the bubble. So what this, if I impose the phase field also, we can nicely visualize with respect to the interface how with each iteration or with each time step how it is refining the mesh around it. So now if I want to further increase or sharpen the interface, I will increase the upper limit and lower down the lower limit, and I will increase this to suppose 60,000. So from here I will delete all the time step. Now here also I'm not changing the mesh, means the block mesh, the steady mesh. So I don't have to initialize it again and again. I'm only changing the dynamic mesh dict file. So if here if you'll see, I'm not changing the mesh. Only we are changing the dynamic mesh file. So now instead of the lower limit of 0.01, now I'm defining the lower limit of 0.001 and upper limit of 0.95 and the maximum cell of 60,000. Now based on this, it will again increase the sharpness of the interface. So again, I will run interform. I can stop the simulation after 1.5 seconds. Yeah, it's better to stop and we can visualize it. Yeah. So you can see at the time step of 0, and there is no refinement around the bubble interface. But just after this, it has started refining. So it depends on application to application and that how well you want to capture the interface. And based on that, you can manipulate the upper and lower limit and maximum cell value. So at the time step of 1.67, it has reached this much height. So if we'll run it further, we can see how it will move out of this domain. So this was all about capturing the bubble interface and the droplet using both static mesh and adaptive mesh refinement. Now, if you have some question, you can ask. Yeah, if you have any question, you can unmute it and
Sir, excuse me,
yeah,
am I audible?
yeah, you are
So,
audible.
sir, if we want to rotate the whole domain, is that possible?
Whole domain like?
Like make it as a rotating box.
Oh, rotating box. Yes, 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 you can do it. So it's better to explore the dynamic mesh dict file. So in my dynamic mesh dict, in this, I have shown how to refine the mesh based on the alpha value. So in the dynamic mesh dict file, there are various options. Means you are saying that with respect to simulation, how it will start rotating, right? Hello.
Hello.
Yeah.
Actually, there is a y-axis there. If I
Huh.
want to rotate around y-axis, suppose.
So with simulation, it should rotate. Or how?
This is but just I have idea. Suppose if this
You can
domain
rotate it.
is.
Yes, using dynamic mesh file, you can rotate it. Yes.
So what should I change? Can you please illustrate
Okay,
that?
so uh, that's what I was asking. Whether you want to simply rotate the file and see the dynamics of flow, then you can simply change the block mesh file. Okay, or using this, if you don't want to change the dynamic mesh file, you can use transform points command.
Is there any tutorial about this rotating domain, suppose?
Let me check. If it will be there, we'll post it. Okay. And regarding which case I have used for the today's tutorial or demo session, you can refer this test case, which is given in the research migration project. So if you'll see, if you go to Forces site, there is completed research migration option is
Yes,
given.
I have.
And this 45th one, you can refer this. Okay.
Okay, thank you.
Hello.
Yeah, hello.
Actually, your screen is not visible.
Oh, okay. Sorry. Oh. Okay. Now it is visible, right? Yeah. So
Yes.
you can refer this one under research migration project. you can refer this 45th test case. Okay. So in this, the whole test case is given with the explanation how to set up the test case for this bubble rising case. Okay. Which part, sir, you want to see with AMR? Laban. Plaban, sir, you are asking to explain AMR part again. So should I have to explain the whole thing or some specific portion you want to see?
You can unmute and speak as well, Plavan, if you are there. From general block mesh to
Oh,
adaptive.
from general block mesh to, okay, okay. Okay, so this is our block mesh file, starting with defining the vertices. So now it is a single rectangular box, so only one block will be there. And this coarsity of the mesh will be dependent on you. So I've given a very coarse geometry of meshing with 10 elements in the x direction, 20 elements in the y direction. So that's why this much coarse mesh we are getting. I'll switch off this field. Yeah. So based on this block mesh file, we are only generating 200 cells in the entire flow domain. But if you want to capture the interface, we are using this adaptive mesh refinement file. And as I've said, it will going to read the scalar field. So that's why we are giving here the field of alpha. But if you have some other scalar field, like in the yesterday session, Ivan was showing how to add the scalar field. So even that scalar field you can use for adaptive mesh refinement. Now we have to define how well we have to capture the interface. So that will be dependent on the upper and lower limit. So you can further decrease the lower limit because anyhow zero it will not going to read. So near to zero value you can give, and upper limit you can give as 0.999 something near to 1. So as you go closer to the actual value of 0 and 1, it will going to capture the domain with that much sharpness. And what will be the maximum cell it will going to generate around the interface, that you have to define it here. Uh, is that fine, sir? Okay, so okay, we'll share the dynamic mesh dig file. Any other question? If no further
Hello.
question, yeah, hello.
I have one question.
Yes.
That is, while doing with the AMR,
Okay.
the initial part of the transient simulation, it is very coarse, right?
Yes, yes.
So is it the means common? Is it common to?
Yeah, it is
all-
common. Yes.
Okay, okay, okay. Thank you.
Yeah.
So just now I have shared the Zoom recording links since yesterday's session, whatever we have done yesterday. So I would request all the participants to download it ASAP, because after no attendance link was given earlier. I'll paste it later on. Just let me explain this. So this Zoom recording link will be exhausted, say after 1 month. So it is advisable that as soon as possible, you all can download it in your own system so that you can refer it in future. Because this is a temporary link, we will be deleting it after some time, maybe after a time of 1 month. But still, it's advisable to download it. Okay, yes. So our team member Paris has just pasted the attendance link once again.
Ma'am, so you're
I hope all of you are, following the hands-on sessions and the lecture sessions, and you are not here only to mark your attendance, because in that case, your learning will be incomplete. Okay. Okay. Yeah. Yeah. Some of you, I am just noticing you are continuously, asking question. You are there online, but it is not recommended that you just join the session only for the attendance sake. Okay, so it is I mean, as a project manager, it is my responsibility to see that the learners who are joining, they are learning it effectively. Okay, so yeah, all the best to all of you. Zoom
s-
meeting download link, I just pasted. Oh, wait. I think, wait, it has gone to somebody's direct message. I'll just paste it once again.
so you're saying that the YouTube streaming will be deleted within a month.
YouTube streaming will be there.
Okay.
Uh, can you
Actually,
explain, sir?
it is
Yes,
going to
ma'am.
some, just a second. So I'll just request the eStudio team to paste it, because when I'm trying to paste it, it's going to some their direct message to Pritika only, and I cannot change it.
Okay, I will post, no problem.
Yeah, thank you. Yes, please carry on. Who was speaking?
Yes,
Sorry for
ma'am. So
interrupting.
some question was there. Yes, Mohit. Yeah, we're going to cover it. How to visualize the data in the para view in the Q&A session.
Hi, Nikhil. Are you there?
Yes, yes.
Exactly. I asked the question regarding the there is 2 points you have mentioned about 0.5, 0.5, and 10, and
Okay,
another
okay,
one
okay.
is minus 10. What is that 10 and minus 10? It is pointing out.
Okay,
It is
okay.
the
So see, we are it's in the 3D. It's a 3D point, right? But we have to solve it in a 2D. Okay, so if I'll
right.
show you uh, the computational domain. So thickness I have given is around, let me see in the block mesh. So thickness I have given of 0.1.
Can you share the screen, please?
Sorry, forgetting this to share the screen. Yeah, screen is visible right now.
Yes.
Yeah. So now if you'll see in the block mesh, I have given the thickness in the Z direction of 0.1 only. Okay. So to define the field, what I have done, I have simply taken it as a cylindrical, initialized it as cylinder, and simply passed on both the side of the domain, or simply allow it to exit on the both side of the domain. So anyhow, we are not solving in the Z direction, so it won't matter unless it is more than the thickness of the geometry. So you can give 2 also, it won't matter.
Okay. Okay. That's my
Okay.
point.
Yeah.
Okay. Thank you.
Yeah. Okay. So, ma'am, if no other questions are there, we can stop or
Yeah, if there are no more questions, we can close the session now and we will meet
okay,
after lunch.
okay, ma'am.
Okay, I hope you have got the attendance link and the Zoom recording link both. Yes, so our eStudio team has pasted the Zoom recording link also. Okay. So in the second half also, I'll be pasting this link. If people who have not joined in this session, they can also access it. Time is we will come back at 2 o'clock sharp, and the next session will be by Mr. Pushkar Sheth of Webtech Corporation. Okay, so please join around 1:55 so that we can start at 2 p.m. sharp. Okay, so we are breaking for lunch now. Thank you so much. Bye.
Thank you, everyone.
Thanks, Nikhil. Thanks a lot.
Thank you, ma'am.
Yeah, thank you. Bye. Hello, everybody. I hope I'm audible.
Yes, ma'am.
Okay. So it's almost 2 p.m. now, and I can see Mr. Pushkar has joined. So welcome, Mr. Pushkar.
Thank you,
Well,
madam.
yes. So yeah, actually we are waiting for more participants to join. So the attendance is around 150 to 200. Yesterday it
Okay.
was 240, and today it was around 190 in the morning. So we
Sure.
are expecting more participants to join. So let us wait for 5 more minutes,
Sure,
and then
ma'am.
we can start. Hmm.
I hope I am audible to everyone.
Yes, yes,
Just
you're audible.
testing.
Yes, yes.
Thanks.
Yeah. So it's 2:05 now, and we have 130 participants. So I think we can start now.
Sure, ma'am. Okay.
Yes. So welcome once again, Mr. Pushkar. So let me just introduce you to all the participants who have joined. So Mr. Pushkar Sheikh is one of the esteemed advisory board member of the CFD team of FOSSI, IIT Bombay, and he is the engineering technical leader at WebTech Corporation. Mr. Sheth holds master's degree in automotive engineering from Coventry University, UK. He has over 16 years of experience in computer-aided engineering, diesel engine component durability simulation using FEA, multi-body dynamics and CFD, high cycle and low cycle fatigue methodologies, utilizing both commercial and bespoke in-house codes. Mr. Pushkar has authored internal best practice document for an end-to-end durability processes for critical diesel engine components and combustion simulation. He has significant contributions in the field through patents on heat exchanger durability and publications on combustion methodology. Additionally, he has authored a book titled Build Engineering Applications Using Python and Flask, and maintains a small open source Python library for 3D FFT called Siglizer. So we are really fortunate to have Mr. Pushkar Sheth with us today. Welcome, sir, once again in this session. I believe and I really hope that this session is going to be a very informative one, a very effective one for the participants of this workshop who has joined with us today. So over to you.
Sure. Thank you, madam. Thanks. Hope I'm audible again. Just checking.
Yes, you're audible.
Sure. So yeah, every time I attend any of the meetings presented or hosted by FOSSI, I am really humbled by the presentations given by everyone else, because essentially I am made to realize that I am not a researcher, not yet. I work in the industry, and I am not supposed to do research per se, not on paper, but a lot of my work becomes like that. I have to find out the right thing to do and all that. So yeah, combustion simulation happened very recently in my career. I started combustion simulation, learning combustion simulation in 2019, 2020. And then took advantage of COVID to deep dive into a lot of it. So yeah, let me share my screen and start my presentation. So let me know if my screen's visible.
Yes, sir.
So yeah, I'll put it in presentation mode as well. So yeah, from the start of my career, I've been working on multi-body dynamics of diesel engines at GE Rail, which was then in 2017-18 called Wabtec Corporation. We moved out of GE, General Electric, and became a separate company. So many critical component simulation methodologies were set by me, and then a lot of work on vibration simulation as well. So yeah, eventually I got an opportunity to work on combustion to support the advanced engineering team. I'm not a part of advanced engineering. I'm a part of base engine team, whose major role is to support durability. But this was a good learning experience, supporting advanced engineering and doing the combustion simulation. So as I said, my interests varied a lot. So I was not doing mere execution when I got a chance to work on combustion. I also started developing in-house methodologies for pre and post processing. So I will try to cover a few of my contributions along with this. So I'll go to the index page of my presentation. So yeah, my presentation is based on a paper that we wrote in collaboration with Argonne National Laboratory. So we were working with one of the scientists at Argonne, and he helped us set the methodology for combustion to select the right knobs in order to simulate diesel engines. Now, obviously, the question with our internal research team was, why should we do combustion simulation? I mean, what is the motivation? Why should we fund it as an industry? So that part I will spend a single slide, and then I'll move to the bits of what were covered in the paper. So CFD methodology. Now this part is covered in a single paragraph in the paper, okay, but I tried to elaborate, given the audience here, given the interests of the audience. They would really like to dive a bit deeper into these things, and some of it I just skimmed through the earlier presentation by Arnab. Really good work by Arnab at TCS on droplet dynamics. Some of the previous work from where his work is derived is applied here to some extent, I believe. Yeah. And then after elaborating on all the numerical algorithms or submodels as they are called, I will move on to the practical part, the application part of it, where I describe the domain geometry and the need for grid generation and independence, and then how we derive the boundary condition with the resources that we have, and how do we set the rate shape. So I think rate shape I will touch upon in the methodology part as well. Further, the last part will be the results of the simulation as they are, the way they are covered in the paper. I will try to show how we got good correlation without a lot of literature in place for large bore diesel engines. So yeah, let me go through it one by one, and yeah, let's go for it. So why is combustion simulation necessary? Why did Wabtec decide to start funding it? Number one, our fleet is huge. We have thousands of machines running in North America. We have almost 800 machines, 800 locomotives running in India that were manufactured by Wabtec in India itself. They were assembled in India, to be accurate. And what diesel engines do is they cause emissions, and the legislation dictates that the heavy industry or the diesel locomotive field is the most difficult to decarbonize, and there are plans in place to reduce greenhouse gas emissions by 2030, 50% reduction by 2030, and net zero emissions by 2050. So yeah, all the best to everyone involved doing that. I hope some of us will also be involved in doing that. But yeah, this is Wabtec's attempt in starting to develop the capability for that. So what is a large bore diesel engine? A small bore, which is used in, let's say, starting from lawn mowers to automobiles, is 80 to 100 mm bore diameter. Medium bore would be used in trucks and small ships, 100 to 150. And large bore will be above 150 millimeters bore diameter. That is the cylinder diameter in which the piston reciprocates. Everyone knows that. That is used in locomotives and then tugboats, large ships, many other bigger engines manufactured by our competitors or level players like Wärtsilä and other people. They have much huger engines than us. Okay, so yeah, then another important purpose of performing combustion simulation is to correlate input parameters with global performance parameters. Global performance can be IMEP or combustion efficiency or other things like heat release and other performance parameters. Uh, Also, once the method is very successful, which takes a long time, we reduce experimentation. But this particular sentence can be, debated, because given that we are pushing for usage of new fuel and everyone's working on hydrogen currently, reduction in experimentation will take a longer time, because we need a lot of data from physical experiments, to make sure that eventually we do combustion correctly on the new fuels as well. So reduced experimentation is a byproduct which may come much later in the cycle, not very immediately. And then, as I said, I touched upon this. Lot of literature is available on small and medium bore diesel engines, but when we started, very less amount of literature was there on large bore diesel engines. So we were, up to some choices. Some choices were open, some knobs were not tried out. What will work well for diesel engines? Although the technology definitely existed, we needed to fine tune that. So that is why this effort was started back in 2021, 22. So yeah, now, because we manufacture engines, we setting up an experimental facility was called for. So the experimental setups are single bore diesel engines. Usually whatever we send out, we manufacture and we send out to our customers are V12 engines, V8 engines for higher power where needed. But the experimental setup cannot be a huge engine. It's going to occupy a huge landmass, because they are all 30-ton engines, and you cannot run experiments. You cannot afford to run experiments on such a big engine. So you have a single cylinder setup, which has all the intake and exhaust pressures calibrated to the way a single cylinder will see in the V setup. Okay, so that is about the experimental setup. Now we have two engine families. You can go to the Wabtec website and see the type of engine families that we have. I have not made it a part of this presentation because they are already available out there. So we took one of the engine families because we already had an experimental setup in our one of our labs, or one of our factories in the US. And exact replica of that single cylinder setup was built on 1D simulation using GT Power. I'm sure many people know that tool. It's a 1D simulation tool for simulating performance and generating performance parameters for various fuel recipes, and the software is trusted to give out good emission parameters also. So we take advantage of the experimental setup and the 1D simulation setup, so that our 3D simulation gets very good curated data from these two sources, and we get a successful 3D simulation. Right. So yeah, I'll dwell more upon this with good images in the later part of the slide. Now I'll move to the slightly difficult part. Now, as I told you, this piece forms a single paragraph in our paper, but I try to dive deeper in interest of the audience here. So for spray modeling, CFD, most of it is established. You in the engine cycle, you have an intake stroke, you have a compression, and then a power stroke, and then exhaust. If you just want to model it without any fuel interference, you can do it easily with the regular CFD algorithms with the turbulence models and the finite volume method together. But what complicates combustion is the spray simulation. The injector getting injected right before TDC, during TDC, and a bit later after TDC as well. So for spray modeling, we start off with blob injection model at the start of the injection, but we don't use the entire algorithm. The blob model uses bag breakup and then shear stripping, but we only assume that the spray is in small diameters compared to the size of the nozzle. They come out in blobs of a single diameter, and then we move to the KHRT algorithm to simulate the primary and secondary atomization. So KH is used to track the liquid core. I mean, what is assumed is the entire liquid core is a one single body, and the KH algorithm acts because of the instabilities at the jet surface, which causes the jet to disintegrate. And then there is a transition. From this, the cohesion is lost and the fragments start to develop. And then away from the nozzle, the droplets can experience both. The bigger chunks can experience KH, and the smaller chunks can experience Rayleigh Taylor. So that algorithm, both the algorithms compete, and whichever algorithm is the quickest, whichever converges the quickest wins, and that is how the spray atomizes in the domain. Okay, so this is a bit of a comparison. So although in Converge, we use Converge CFD for our combustion simulation. So at the start, of course, the blob model is used, but for primary and secondary atomization, the KHRT model is used. And I will try to list the aspects of each of it. So in the KHRT model, the liquid core is tracked, and then it's tracked only until the core is broken. And then the mesh sensitivity. So one I wouldn't say disadvantage, but one requirement of the KHRT model is it will require a slightly finer mesh than the blob model. The blob model is grid independent because of the bag breakup and the stripping, but KHRT needs a slightly finer mesh, at least in the spray cone, so that all these these atomizations can happen in a bit more detailed manner. So yeah, going next, once the spray is atomized and we have finer droplets or droplets of a certain size, we have to also implement a droplet collision algorithm. Now the engine that is simulated and also experiments have been conducted is a 6-hole injector. Let me just check that. Yeah, it's a 6-hole injector, and when two injectors fire and the spray come from each other, the drops need to interact with each other. They cannot just merge into each other and not cause any other effects. Those effects need to be captured. So the NTC counter by Schmidt and Rutland is implemented. So you can, based on the Weber number of the, based on the speed of the droplet, either they can merge, based on their trajectory, they can bound, like rebound elastically. And then if they are too fast for each other, or if their trajectory is too obtuse, then they can break up as well. So The NTC gives a couple of advantages because the collisions are tracked statistically, and random sampling is used instead of checking all the pairs, because if you start checking all the pairs, it's going to take a huge time for the simulation to convert. The time step may drop a lot, and you spend a lot of time there. Instead, you track only a handful of collisions statistically, say 100,000 to 500,000, and that is how you quicken the simulation. And then there is trajectory based selection. So if the droplets are moving perpendicular to each other, they are not going to collide. If their trajectories are sort of matching, then only the collision algorithm is applied to it. So that is another advantage here. And as I told earlier, the Weber number is used to decide whether they coalesce, whether they graze, or they bounce off each other, or they coalesce into each other. So yeah, this is also another implementation here. Yeah, and then O'Rourke is also used in some places. It is not entirely eliminated. Like if we have droplet to wall interaction, O'Rourke algorithm is implemented. Here it is not entirely ignored. Only for droplet to droplet interaction, we have Schmidt and Rutland. And droplet drag model, we use a Lewis model. I'm not covered it as a part of this presentation, although. So yeah, where O'Rourke is quicker, it is used. It is not used for drop to drop interaction, but it is used from drop to wall interaction because it is better there. Okay, rate shape algorithm. Now in all these works, all these research was a part of someone else's work. Okay, but what did Pushkar as an engineer and a non-researcher do in this work? So my contribution here was this rate shape algorithm. So I'll try to explain. Let me see if my pen works. Yeah, it works. So what is a rate shape? Now when say this is the injector, okay, and there is a so-called pin here, okay, and this pin here in case is controlled by a solenoid, okay, and the solenoid is provided a current, okay, so the current looks like this, something like this, not precisely, and then after a certain period of the solenoid starting, the rate shape starts to develop, okay. So this particular rate, although it is a supplier part, the supplier was very kind enough for providing us rate shapes for many pressures. So we have rate shape is a function of what? It's a function of pressure, nozzle diameter, density of the fluid, and yeah, I think these many. If I forget, I'll come back to it. But then, so what I mean to say is we have a lot of data for this rate shape with various timings. So this is time in terms of crank angle degree, and we have rate shape in terms of velocity in meter per second. Okay, so we have a lot of data like this, okay, at various pressures. Let's say this is 1800 bar, this is 1600 bar, and let's say this is 1200 bar, and lower ones can go as low as 800 bar. Okay, so these are the lower side. So for now these injection pressures, they are based on the notches. So in higher notches, of course, what do I mean by notch? Notch is engine speed, okay, simply put. Now if you have seen any locomotive movie, I can point out Denzel Washington's Unstoppable. Okay, if you have seen that movie, he talks about which notch did you leave it at? Which notch did you leave it at? And that fat locomotive driver, he tells, I left it at full notch. That is notch 8. That is the highest notch a locomotive can have. And the highest speed the locomotive can go at. Okay. So for notch 8, 800, 1800 to 2000 bar will be used. Okay, so I let's say I took data for 1200, 1600 and 1800 bar. Now we had a task. We wanted to from test data, what we have from test data, we capture only the solenoid current. Okay, we capture the solenoid current, and from the corresponding solenoid current, we also had a rate shape. We had these two data, and we had the duration of these two. This is the duration of current, and this is the duration of the, this is exaggerated, okay, not, it's not going to last this long, but this is the duration of the spray. Okay, and then if you draw a plot between duration of current and duration of spray, it will sort of come out like this, 45 degree with some scattered here and there. Okay, so what my job was, if we are given a solenoid current, you predict a duration of the spray for that particular pressure, for that amount of holes, and keeping in mind the density. So I started parameterizing all these curves. I had about 30-40 curves for 1800, 1600 and 1200 bar, and I started manually parameterizing each of them. I took 3 weeks, and then came out a simple Python function where you just input the pressure, you input the nozzle diameter, you had an option of giving the coefficient of drag at the injector tip. Okay, that is, I won't dive deeper there here in the interest of time. And then you give the density of the fluid also. Now, why density is important? Because during testing, the density of the fuel used may be a bit lesser than diesel. They might also not use diesel. They might use a different surrogate liquid, just so that they don't waste money on diesel. So we need to have a ratio of density between the test fluid versus the fluid we will use in the engine. Okay, so I wrote a Python function wherein you just give these 4 parameters, and boom, it will give you a curve, and it will give you a duration. It will predict a duration that you can correlate back to your injection timing. Okay, so this was version 1. Okay, I was doing too much manual parameterization here to get this sort of curve, and it was restricted only from 2000, let's say anything about 800. So it also worked for 2000 luckily, and only up to 1200 bar. This algorithm worked only for 1200 bar because I parameterized only that data. Now this was version 1. Okay, version 2, which version 1 was done sometime in 2021, just before this paper was written, because I gave the data from this algorithm for this paper, the iterations for this paper. Version number 2 was programmed this year. Now this year task was okay, I will jump the gun here and say that why version 2 was required. Version 2 was required for capturing smaller quantities of fuel, because we decided to start simulating dual fuel simulation. Okay, now dual fuel is using any other fuel including hydrogen for our simulation. So we started getting rate shapes for diesel for smaller amounts, because the rate shape for the other fuel will also start increasing, although that data is not available. But for the version 2 in 2025, I used another strategy which parameterizes the entire curve. Okay, and then based on the same data it will give out, but it will work for lower durations also. Only thing is it was not hard coded as the version 1. I used a bit of neural networks here to bring up include the lower notches also. Yeah, so it took a bit of time to run because it is running a lot of calculations back end, but yeah, I sort of improved. So yeah, this is my big contribution in the entire field of combustion simulation at Webtech. So yeah, going ahead. So yeah, how does this liquid transition to vapor in the simulation? So for a liquid surrogate, um, we use liquid properties of liquid which are marked as diesel 2 or N tetradecane, for which all liquid properties over temperature are given. Okay, like vapor pressure, specific heat, viscosity, all those properties are given. And we use a chemical surrogate which are chemical species, and they contain all the gas related equations. These are obviously everyone here knows about them. They are chemical kinetics mechanisms. We started off with using N-heptane, but I think which is covered in this paper, but eventually we ended up using N-dodecane. So that is the Wang mechanism by sorry, University of Wisconsin. Guys, give me a moment, please. I need a glass of water. Sorry.
Sure, sir.
And the ladies, of course. I'm sorry. I'm back. Sorry about this short break. Yeah, so where was I? Yeah, I was at chemical kinetics mechanism, and the Wang mechanism is what we have stuck to over the years because the diesel combustion was very good, very nicely simulated with Wang's dodecane surrogate for diesel. Right. So yeah, let me go ahead. Okay. So then we move to combustion modeling, and one option is we can use the Sage combustion solver, which will work on every cell, but it is very computationally intensive. So we use something called as well-stirred reactor multi-zone combustion modeling, which is available in many softwares, but it is also implemented in Converge CFD. So so yeah, what the well-stirred reactor multi-zone model does is it divides the zone into various. It divides the combustion domain into various different zones according to temperature and equivalence ratio. Okay, and into various based on the like based on what status it is at, what state it is at. Is it unburned? Is the fuel evaporation in these zones? Is the premix happening in these zones? Is the burning happening in this zone? Or the products have been developed, the reactions are done, and the burned products are now rotating around in this zone. So it divides them into various zones, and each zone will have their bins. Okay, these bins, of course, as I said, are developed are decided based on the variation of the temperature and equivalence ratio. And I if I'm not wrong, if you stay around the plume, the bin might be equal to the cell zone. Okay, so it can go that small because you need to solve the combustion zone a bit accurately, but the other zone where the air is spreading, you can have larger zones according to their temperature and equivalence ratio. And then you track the mass transfer between the zones, so that you are obeying first law, you are not breaking first law of thermodynamics. So between each zones, when the fuel droplets evaporate, convert from liquid to vapor, you capture the mass transfer from the evaporation to premix zone. And if the premix starts burning, you capture that. When the fuel vapor and the air mix, you capture those mass transfers. When the products cool and then start mixing and form the exhaust gas, that is you move it to the burnt zone, and so on and so forth. Okay, and then eventually heat escaping through the wall. So that also affects the overall temperature of the entire gambit of the entire combustion domain. And then you solve the detailed chemistry per zone. Okay, so again, you per zone, as in you solve it per bin, so that the number of calculations are lesser. You have pre-mixing, burning, and products. You form the bins according to temperature and equivalence ratio, and then this calculation goes much quicker that way. So yeah, once you have the zone temperature and pressures calculated, you can then calculate the heat released by the zone, and then which will also cause increase in temperature. Heat, as covered earlier, heat lost through the walls, compression by the piston, and expansion, which will cause reduction in pressure. Okay, so this we compare with full chemistry, like SAGE algorithm or something, which takes a huge amount of time, but WSR multizone takes a lower amount of time. Converge uses it for both. It can use WSR multizone MZM for 3D simulation. It involves WSR for 0D chemical kinetics also. If you want to develop your own chemical kinetics mechanism, you can do that using Converge CFD, using their 0D tools for ignition delay and 1D simulation for flame speeds and etc. So we have explored WSR. We have also done some simulations using SAGE, where we think it is important to capture it in detail. We have also explored ECFM 3Z, which is another way of making tabular data from the chemical kinetics algorithm and then giving it to the combustion model. You know that your domain is going to go from this temperature to this temperature, from equivalence ratio of say 0.1 to 1.2 or 1.5. You know this, and then you can calibrate your tabular data and then just give it to the combustion model to quicken the simulation more. ECFM 3Z has been the quickest in the lot. Not for this paper, but much later than this, we have also explored ECFM 3Z, which is much quicker than even WSR. So yeah, then turbulence model. I think I don't need to elaborate more here, but our we know how, everyone here knows how RNG K epsilon works. It boils down to basic Newton's laws. So if there is a fast fluid and a slow fluid moving along, there is a viscous shear stress formed between them, is the basic tenet for this. And when between this fast fluid and the slow fluid, a viscous shear stress is formed. Now, Boussinesq hypothesis states that turbulent stress is directly proportional to turbulent eddy viscosity and velocity gradient. So the K epsilon calculates the turbulent kinetic energy and the rate of dissipation, how the these viscous forces are converted to heat here. This is tracked by the RNG K epsilon, and then the RNG part does a bit of analytical adjustment from the analytical coefficients that are fed to it and adjust the strain rate sensitivity from these. But the basic assumption is that for a single flow, you boil it down to an average single eddy viscosity. This works okay for isotropic flow case, because your turbulent stresses are not formed in all three directions in an isotropic flow. When I say isotropic, you can guess it is like a jet flow moving in a single direction. But in a combustion simulation, the flow involves, as the air enters, it causes a swirl. As the air enters from the intake wall, it causes a swirl. It also causes a tumble component, and all those vorticities form a very complex flow environment in the model. So that is, and this becomes more prevalent in a larger bore, because it has more area to move around, and the system pressures are also slightly higher. So that is why, to capture these anisotropies, you do not average to a single eddy viscosity. You calculate for all the six stress components, and then the seventh factor will be the dissipation rate of all these, and a connecting factor between all these stress vectors. Okay. Yeah, this shows that I am not habituated to talking a lot, but yeah, let me move along. Give me 1 more minute to get a bit more water. Sorry guys, and the ladies again.
Sure.
Right, I think I have 12 minutes. Yeah, so as I was saying earlier, RNG K epsilon works well for a simple jet or a boundary layer over a flat plate, whereas RSM would be unnecessary in that case, because you solve unnecessary components of the stress. So you might as well use a simple 3 equation or 2 equation solver. When there is a swirling flow or a vortex, that is where RSM comes in play. So a curved duct or a turbo machinery application where you have the volute or you have the impeller, you have many stress components happening. So that is where RSM proves. Now, in this summary, diesel, it says reasonable with calibration, and which is true, which we will also observe in our results. But RSM makes it a bit more better. It takes the result slightly towards the better side. So yeah, let's move to the results quickly. Yeah, there are numerical models. This is obvious for any CFD. We use Navier-Stokes equation for mass, momentum, and energy balance using the finite volume method. We have the Rye-Chow scheme to store all the computed values at cell centers. We use PISO for solving the transport equations. And then we use an adaptive time step. Adaptive, it should not be adapter. Adaptive time stepping, and then non-ideal gas behavior using Readiness. So yeah, I won't dive deeper here. These are boilerplate. These are used for majority of the fluid flow simulations. So yeah, diving into the application part now. This is the major chunk of the paper, which occupies 4 more pages. I'm sorry about that. So yeah, this is the domain geometry. As a industrial company, we have all the CAD models with their proper tolerances made. So we extract the flow volume from there. As I said, we have a 6-hole injector and a piston here. So yeah, this is the geometry we have. And this is as required by ASME. I am referring to the paper. I'm the first author here, so I can use the images from the paper here. So yeah, then we go to grid generation. So as I explained in the KHRT model, for the spray we need finer grid. So we sort of tested out 3 types of grid of 0.5, 0.25 and 0.125, and these are the images you see of the slice of the domain. Now these there is embedding in the spray region, which only switches on at -15 before TDC, -15 degrees before TDC, and then goes off at 30 or 40 crank angles after TDC, because it's unnecessary, grid unless you want to capture the spray. So when the spray is on, the grid embedding is refined. And then we also use automatic mesh refinement, which is now I think also available in OpenFOAM. But this is a Cartesian grid with cut cells. So at the boundaries of the piston and other places, the cells are cut. And you have automatic mesh refinement for temperature and velocity gradients also in the spray region when the spray is happening. The AMR also cuts out after some time, so that it does not waste a lot of time during intake and exhaust stroke. And you see here in the bottom graph that with reducing mesh size, the number of cells in the domain increases a lot, especially just after TDC. So 720 is TDC for us. So just after TDC till 750 it goes high, and then you switch off one of the embeddings. Sorry. So yeah. It reduces after switching off one of the embeddings. So the cell count reduces here. Then the inlet outlet boundary condition. So yeah, this part is a bit involved. I showed you 3 boxes earlier: experimental data, 1D GT simulation, and 3D CFD. Now in experiment, we capture the temperature and pressure inside the cylinder. Now that temperature is very difficult to capture using thermocouples, because they vary throughout the cylinder, and a thermocouple will only capture in the vicinity. But pressure is something that we can trust from the port mounted pressure measurement. So we assume that we have only the pressure using our ideal gas laws. We can also calculate the temperature there and hence the heat release. We also have this GT model, wherein if we give this heat release, it will back calculate the pressure and temperature for causing that heat release, and eventually give us an inlet and outlet boundary condition, keeping in consideration all the velocity correction factors required at the inlet and outlet. So what you see on the right is the motored and fired. Motored are in green, and fired temperature and pressure are in magenta and red. respectively, and at the inlet and outlet. Okay, so we start with a motoring simulation to make sure that the motoring is generating a correct pressure. So I'll go to that. Now in the motor simulation, we have two options. We use the lower wall temperatures and the higher wall temperatures. Lower wall temperatures are the one captured after significant time of stopping of the combustion in the simulation. We have thermocouples at couple of locations, couple of millimeters deep in the cylinder and the piston stroke location at the liner. So we have the lower wall temperatures and the higher wall temperatures. What we see in the motoring is the higher wall temperatures come close to the experiment. So we stick to using the higher wall temperatures for the fired simulation also. So then we perform a grid convergence, but when we were doing this grid convergence, we were using RNG K epsilon. So that is why we had a bit of a mismatch here. You see, the heat release did not match up with the experimental heat release. Now, that caused a lot of questions, because why is the heat release not being simulated? And that is where the trials of RSM came into picture. So once we go to RSM, first thing we observe about the spray is the liquid penetration became slightly better, as we see here, and the vapor penetration became lower. Okay, so everything, all the vapor did not go and hit the walls. Okay, that is another thing, because another observation, because what would be happening is when the plume develops or when the fuel is sprayed out, the combustion starts at the periphery of the plume, and that is where all the eddies start forming and not reach the the surface, which causes reduced heat transfer and hence a better heat release. Okay, so then we started matching up with the experimental heat release. We tried three different starts of injections. So now the 13-13.3 was the one used earlier in RNG K epsilon. We went slightly advanced and slightly later also. And all the three cases, we found that there was still a bit of difference in the RSM and the experiment, but it was much better than the RNG K epsilon. Okay. So yeah, I hope this made sense. And then eventually we have global performance parameters like indicated mean effective pressure and thermal efficiency. So first we look at combustion efficiency again for all the three advanced injection advanced timings. We see that RSM fares much closer than experiment, although RNG is not much different. Now a question may arise here is how much more time did RSM take than RNG? And we did not see a lot of difference. There was only I think 6% difference in the time required to solve RSM than RNG. 6 to 8%. Okay, not a lot of overhead because of RSM. Okay, so and then we go to IMEP and indicated thermal efficiency. Those are also the same thing. RSM fares better than RNG K epsilon, and RSM is closer to experiments. So yeah, I think I'm almost on time, right on time rather, with all the coughing and all. I'm sorry about that.
No, in fact, we are thankful to you that with such heavy cough and cold, you have managed to, deliver such a brilliant lecture.
No, it's not a cough and cold. कहाँ से आ गया मालूम नहीं है. Maybe I was so nervous.
Some
before.
allergy maybe.
Yeah.
Okay. No, actually, you can take some more time, ma'am, if you want.
No,
We
I
are not
think that
in-
was my last slide. I'm
Okay.
done actually. Yeah.
Okay. So, people who have joined now, you can ask any questions to Mr. Pushkar.
Yes, please.
Yes, you can go ahead. You can raise hand and go ahead.
Thank you.
Somebody
Hi.
has been-
Yes. So yeah, my name's Shaw. I'm all the way here from South Africa. I was just wondering. I've heard of this Converge CFD software. It's quite nice. I've seen a lot of it. What it can do, especially like on LinkedIn and marketing. I was just wondering, how have you ever tried open foam, or what was the challenges maybe had with using any open source software CFD for this kind of combustion work?
I am very much interested. I didn't catch your name, sir, but yeah, I am definitely interested in exploring open form, and I also pitched it internally. But at the moment, they would like to continue with Converge because it's a flagship offering, and open form, although being open source, it may not have the fidelity to solve these complex scenarios, but I'm definitely trying to work something towards trying to develop on open form. Yes.
Cool. Thank you very much.
Cheers.
Chat box.
How
do
do
you
you
integrate?
integrate experimental data with CFD results for model validation? Right. So, what will experimental data capture? It will capture the inlet temperature, inlet pressure. It will capture the in cylinder pressure. You have the in cylinder pressure from the testing, and then from the exhaust you have the exhaust. Yeah, sorry, can I continue?
Yes, yes, please.
Yeah, so Mohit, I am trying to answer here. So we have the pressure from the in cylinder, we have the pressure from the combustion simulation, we compare the pressure, we compare the heat release rate like we have done here on my slides, and then we compare cumulative heat release, that is nothing but adding up the apparent heat release at every step. And further, if we have a calibrated emission measuring setup in our test, we also go ahead and compare emissions, but at this stage they are very anecdotal. So we don't have a robust way of predicting exact emissions, but we can definitely compare trends. That is what we have done even in this project. Only I'm not allowed to capture it here, it was not even captured in the paper. Sahil, okay. How do you change the default parameters coefficients to tune your setup in terms of turbulence models or for? I have not. Yeah, very good question, Sahil. Thank you. I have proposed experimenting and to changing these parameters, like going from KHRT to O'Rourke and other things, but again it's based on what is needed. Do we need to do it at the moment? Is this working? If it's working, let's go with it. As I said, we are not we would not like to be like a research organization, although the, the work might want us to be, but we are still engineers and we just want results that are applicable. So yeah, when I eventually at any point if I become a researcher, definitely I will try to tune this. But yeah, we have tried shifting back and forth between RNG and RSM at many points, and always found out that RSM is better than RNG. you know we have not tweaked any coefficients. No, we have not tried that, sir. Mm-hmm. Okay, some discussion on KHRT. All right. Any more questions? Also for multi-cylinder engines, what piston location is used to compare testing data? We take all the pistons and see what's happening in all the pistons, and every time we get test results we will find that one piston was not generating any combustion. Okay. So yeah, I give it a funny twist here, but those are realities of having experimental data. But we take an average of all the cylinders, Sahil. If we have multi-cylinder data, we have all the data, we put all of them on a plot and see what is happening. Large volume combustion for HCCI engine possible. Can you remind me what HCCI, high compression, what is that? Navant. Homogeneous charge. Does homogeneous charge mean that you premix the fuel and then pass it to the intake manifold? Sorry, I don't know the term, but am I right? You mix it in the intake manifold and pass it to the cylinder? So yeah. So if when we do dual fuel, that is the first strategy to test if the second fuel is working properly or not. So for example, we start with methanol. Okay, methanol is our secondary fuel. We choose a substitution rate of 50. First thing we try is we put a collar on the intake manifold and start giving out some amount, start introducing some amount of methanol, let it mix in the intake manifold, and then let it through in the combustion chamber. Same with H2 as well. We pump it in the intake manifold, and then at whatever substitution rate we decide, we have tried till 60 or 70, and then we let the intake walls open and take it to a compression unit. So yeah, combustion simulation is definitely possible. Why not? Mohit. Yeah, you send me an email on LinkedIn, boss. I'll help you. Okay, I guess these are all. Any other questions, you can reach me. I am pretty approachable. And yeah, of course, if you find any mistakes in my presentation, do let me know. I'm open to those feedback as well. Thanks, everyone.
Do you have any more questions? Of how we can reach out of that you can answer, Mr. Pushkar.
Yeah. You put my name on Google, you'll find a couple of ways of reaching me.
Okay, so if there are no more questions, we can wind up this part of the session. So thanks a lot to you, Mr. Pushkar.
Thank you, madam.
Thank you once again. I hope this is a very, most of the learners could follow whatever you have said, and some of them has appreciated it heavily. So thanks a lot. Very informative session.
Sure. Thank you, madam.
Thank you. It is okay. Laman Sen has typed something. Yes. So thanks a lot for your efforts once again. We'll wind up this session now and we'll go ahead with the demonstration part, the hands-on part by our team member, Mr. Manjil Situla. So Manjil is working with the FOSSI team from Nepal. Okay, so what do you, Manjil?
Thank you, ma'am.
Okay, so you can, over to you. You can start the session now.
Okay, ma'am. Before starting my presentation, I would like to thank Pushkar sir for such an insightful session, which taught many small things related to combustion simulation and display modeling as well. So the presentation showed how choosing different turbulence models can affect the accuracy of the simulation and the results itself. So that was very sophisticated lecture, I would say. Now we will try to simplify those things in this demonstration session. So welcome you all to the CFD workshop on combustion in a piston engine using OpenFOAM. So it's me Manjil Sitaula, research assistant at FOSSI. So this training is aimed to be a beginner to intermediate level training session, and we'll be doing a tutorial in the foundation version of OpenFOAM, that is OpenFOAM version 9. And please feel free to post your queries in the chat. And also please let me know if my voice is breaking or if I am too fast with the speech and everything. If there is any such issue, then please let me know in the chat box. So the problem definition is we will simulate combustion phenomenon in a 2D axis symmetric ways. So we will be using a 2D axis symmetric waves geometry. So we won't be doing a 3D. We won't be doing a 3D simulation, and we will be simulating the compression and power stroke of an engine. And this is a simplified case, not a 3D piston cylinder. And we will we'll explore the different types of solvers that are available in OpenFOAM and how they fit in the combustion of the piston simulation, and we will also observe the various advantages and limitations of all these solvers. So the first we will be doing is we will be running the tutorial cases. So these are already available in OpenFOAM, and after that we will try to combine the two solvers, so cold engine foam and then reacting foam, and after that we will be using only the reacting foam solver, and then at last we'll be using engine foam, which is a compact solver that consists of all these above solvers quality. So the governing equations involved are the continuity equation, momentum equation, energy equation. So you all know what these equations are. And after that, we will also be the solvers also solve for the scalar transport equation, and for the chemical reaction part, they solve the Arrhenius rate equation, and also for the certain physical properties and data, they also solve for the Janaf polynomial equation. So this all these equations are utilized by the solver, which is coded inside the solver itself. So we will later see how we will define, for the Arrhenius rate reaction, how we will define A, beta, and all these constants like TA, and for the Janaf polynomial equation, how we will define all these polynomial coefficients like A1, A2, A3. These are provided in the Janaf table itself. So we will just have to input the data for this in our physical properties. So this is our geometry. So it is a 2D axis symmetric waves. So we have a piston and we have cylinder head. So which the piston moves, say it compresses and expands. And we have a axis. So this is the axis about which we can rotate and we will be able to form a cylinder. And the liner and the liner will also move with the piston. So these are the boundaries, and we'll also later see in our block mesh how how the boundaries are defined. And we will be using dynamic mesh simulation in OpenFOAM. So mesh velocities is included for dynamic mesh simulations. We need to include the mesh velocity in our general transport equations, like the momentum equation and continuity equation. So we can provide the motion by predefined functions. Like we can provide using how our moving boundary moves. We can provide that by using predefined functions. Like if the motion of the boundary is oscillating linearly, or if it is oscillating if it is rotating, or if we can provide such different type of functions which are available in the dynamic mesh library of OpenFOAM. And for calculating mesh velocity, there are two different approaches. So either we can solve for the Laplacian equation and we can calculate so if we do the FPM of this equation, then we can calculate the mesh velocity, and we also have the boundary conditions for to solve this equation for mesh velocity. And this mesh velocity is inputted in the general transport equations. So this is one approach by solving the Laplace equation. And the another approach is we just track the geometrical mesh movement, or just we track the movement of the points of the mesh and then calculate the mesh velocity instead of solving any equations. So for the Laplace equation, we need the value of diffusion coefficient also. So how the mesh is diffused, how the mesh motion is diffused in the domain. So this diffusion coefficient handles that diffusion thing. Okay, so this is our first case structure. So first we will look at the tutorial case that is available in the OpenFOAM. So before that, I would like to highlight the highlight the difference between two solvers. So I have here the cold engine form solver, and on the right hand side I have another solver called the reacting form. So you can see that we can note that the cold engine form is does not solve the combustion or the chemistry part. So in the case structure, you can see that there is no any file called the chemistry properties, combustion properties, and reactions files are not included in the cold engine form. And but for the reacting form, the solver this solve for the combustion. So we need to specify the different species in the chemical reaction. We need to define how those reactions are solved in the chemistry properties and the combustion properties, and the reactions itself. What type of reaction is that? Is it a simple reaction, or just a chain of reactions? So we need to specify those things in the reactions file. We'll later see how these are specified. And one thing to also another thing to note is that the cold engine form, it do not solve for the scalar transport. So drawback of cold engine form. So the scalar transport is not solved by the cold engine form, but the reacting form, these solve the scalar transport equation. So let's see what I mean. So I'll show you in the solver itself. So I hope my screen is visible.
Yes.
Okay, so let us go to Ubuntu. So if you after we go to Ubuntu and our installation directory of OpenFOAM 9, so it is located in OPT. And if you get inside OpenFOAM 9, and we can go to applications and solvers, and then combustion solver. And there are different type of combustion solvers. They are came from cold engine form, PDR form, reacting form, XI form, and I think there is also spray DYM form in another version of OpenFOAM, like the latest versions. It also consists of spray modeling. So in our presentation, in this demonstration, we have not modeled any the spraying of the species. So that is a different complicated topic, like Pushkar sir said. So we will try to work on that. And another thing is this spray modeling is now being worked by an intern at FOSI itself. So an intern is working for the spray modeling under Pushkar sir himself. So by the next workshop, hopefully we will be able to present his case study for the spray modeling. So let's go inside cold engine form, and if you go inside cold engine form, and if you go inside the .c file, then you can see that we have included the U equation, we have included the rho equation, we have included the energy equation, pressure calorimeter equation, all these equations, but there is no mention of the scalar transport equation. But if you go back to reacting form, so in the reacting form, if you see that there is an additional equation called Y equation, so this equation, actually this part is where the of the scalar is solved. So this this equation is not included in the cold engine form. So we can either modify the cold engine form solver to include that equation, Y equation. We need to include the header file as well, and other considerations or changes can be made to okay. So these are the two differences I wanted to highlight. And after that, another difference is we can see that the cold engine form solver, it can use engine mesh, which is a layered mesh approach. So this engine mesh, it does not it is also dynamic mesh strategy, but it is not under dynamic mesh library. So this is a separate library for piston related simulations. So for IC simulation, I think we have a folder called we have a library called engine in the, if you go back and if you go to the src file where there are the source codes, so we can see that there is a folder called engine. So in this library there is a library of engine mesh, which is a layered mesh approach. So but this engine mesh, this cannot be used with reacting form. So we need to modify either modify this reacting form to include engine mesh. But in the tutorial, in the solver, in the current solver setup, the reacting form, it do not read engine mesh libraries. So for if you want to set up in reacting form, we need to set up the dynamic mesh using dynamic mesh dict. So these are the two differences in the cold engine form and reacting form solvers. So now let's go to our case. So this is our case that I would like to present. So first of all, I would like to present the tutorial case. So these are the two tutorial cases that is available in the open form itself. So if you go to your installation directory of OpenFOAM version 9, so you can see that there is a folder called tutorials, and in that tutorials you can go inside combustion. And inside combustion there are different tutorial cases. So if you go inside cold engine form, there's a free piston. So you can see these cases. These cases are copied to my another working folder. You can also copy into a run directory to run this simulation. So it is just a tutorial case. So let's run this simulation first. So first, let me open my terminal and launch Ubuntu. Now I'm sourcing my OpenFOAM 9. So first of all, let me move to mesh, block mesh, and let me show the mesh. So this is the geometry that I had shown in my presentation. So this is our geometry. This geometry is already available, pre-available in the tutorial cases all yourself. So let's see surface with edges. So this is our structured hexagonal mesh. And as I had mentioned, so we can see in the block mesh dict. So this is our block mesh dict where we define our geometry and the mesh. So I think this is a simple geometry with a single block, and which extends from 0 to 0.05 in the x direction, and in the y direction from minus 0.008 to plus 0.008, and in the z direction it extends from 0.0 to 0.13.
Manjeet,
So
please increase the font size.
okay,
Yeah, it's fine.
is it fine? Yeah. So this is our geometry. So if you also want to see in the paraview, so just you can turn on axis grid, and if you turn on the axis grid, and you can see that the geometry extends from 0 to 0.13 in the z direction, and in the x direction from 0 to 0.05. So in this way you can visualize geometry in paraview to see if the coordinates are matching. And one thing to note is we are using wedge condition. So when using wedge condition, it is always required that it requires that in the wedge direction the number of cells should be 1. So we have kept the number of cells as 1, and we have not used any different grading parameters. We have just used simple grading, that is the even mesh is being generated, and we have defined front and back as a wedge. So if we are doing a 2D planar simulation, we will define front and back as empty, but since this is a 2D axisymmetric wedge geometry or wedge simulation, so we need to define front and back as wedge, and these are the boundary faces. So I don't think I need to explain how to define all these boundary faces, the direction that we need to choose to define these faces. So you can work around this on your own. And axis we make it as empty. And other thing is, so front and back as wedge, and piston will be wall. So it is a wall that moves. So how do we how do we know that the wall is moving? So we will incorporate a boundary condition in the velocity file. So we have a velocity boundary condition called moving wall. So this moving wall boundary condition will accompany for the movement of piston. And cylinder head, it will be it is wall, so it does not move, it is static, and axis is empty, and liner is also a wall. So this is just we are compressing the piston, and the mesh will deform and compress itself. So this is our block mesh dict. It's a simple single block geometry. And after that, let's look at the boundary conditions. So we look at the boundary conditions. So you can see that in the cold engine form, as the cold engine form do not solve for the specific species, so there we do not have any files related to the individual species. So so here in this case structure, we can see that there is no individual species file, but in the reacting form, since it solves for the individual species and also the chemical reaction or the combustion, so we need to define these species also. So the boundary conditions will be the same for all these cases. So I'll only explain the boundary condition for a single case. So let's look at the U boundary condition first. So U boundary condition, we have the front and back as wedge. So this is wedge boundary condition, and it is saying that for the liner, the boundary condition of U should be included from the include folder, case settings, and wall U. So if you go inside the include folder, case settings, so and inside these case settings also it is asking to include the boundary condition. So if you again need to the reference it is referencing this boundary condition file. So if you look at the boundary conditions, so what this U is saying is you need to include from the case settings wall U. So in the case settings itself, there is no mention of wall, but it has referenced this file also, so we can check it here. So go to wall sub dictionary. These are the sub dictionary inside the dictionary boundary conditions. So go to wall and go to U. So take this boundary condition and put it in this U file. So it is saying that. Similarly, for cylinder head, just take the boundary condition from the liner boundary itself. So this boundary condition, just you take. So you note that we need to include a dollar sign here to include the boundary condition of another boundary. And for piston, so you can see that you include from piston U. So if you see at piston U, so let's see at piston and U. So we can see that there is a boundary condition called moving on velocity. So this boundary condition is very, very important in dynamic mesh simulation. So what it does, it does not set the wall to zero velocity that no slip does. So what moving on velocity it does is it will set the wall to the moving boundary velocity. So U at wall will be U at moving equals to U of the moving mesh. So this U does this boundary condition does that thing. So after the U is set up, so let's look at the temperature. So similarly, the temperature uniform field. So if you go at boundary conditions, internal field. So it is saying for the temperature it is saying referencing to include case settings internal field T. So case setting internal field and T. So it is setting the temperature to 350. So you note that. So this is a cold start simulation. So we have a very low temperature, nearly near not much high temperature than a hot start. So we can also increase this temperature to see the differences that this internal field temperature will do in the simulation. So we'll also see these things in the later cases. So these the temperature ones. You can check this in your tutorial case. So I have not changed anything for these boundary conditions. So UT, and after that the pressure boundary condition is also the same. So you can check at the boundary condition of P. So internal field we have initialized with P initialized with 1E5, so atmospheric boundary condition. And other thing is the type wedge. So note that every front and back we have in every boundary condition we have in every boundary file we have used front and back as wedge. And liner wall P. So you can check out these boundary conditions. So these are the normal, the simple boundary conditions in every cases that is used in OpenFOAM. Now after that, this is running. This case is a turbulent simulation. So to see if this is which type of simulation is this, so we can just open the momentum transfer file, and looking at the momentum transfer file, we can see that this is a it is a RANS model, and RANS model it is using K epsilon. And for the K epsilon, so if it is using K epsilon, then we need also the wall functions, because in the because the first cell height would be very greater and will lie in the log law region. So we need to model epsilon using epsilon wall functions in the wall. So if you go back to the boundary conditions for epsilon, so this is in internal field epsilon. So if you go at the case settings, so this is the value. So this is already calculated and provided in the tutorial case. So if you want to see or learn how to calculate these values, so there is a good tutorial and good reading material in the FOSI website under this spoken tutorials. So there is a tutorial session on turbulent modeling. So you can see that tutorial, and also there is a additional reading material. You can access that additional reading material file. It has shown the detailed way of calculating epsilon and k value and nu t value. So you can refer to that file. It is in the FOSI spoken tutorials website. So alpha T is a turbulent thermal diffusivity. So it is calculated from nu T. So nu T, before that, let's look at nu T. So nu T is the eddy viscosity. So K epsilon actually is the eddy viscosity model. So nu T is calculated. It is calculated boundary condition. So if you go to wall nu T, so let's go at wall and nu T. So we need to provide nu T wall function at the wall. So as I've already said that wall functions are required because the y plus because the first light will lie in the log region. So similarly for the epsilon at the wall, so we need to use epsilon wall function. And for the k, that is the turbulent kinetic energy, we also need to use the wall functions. So different type of wall functions are available in open form. So this kqr wall function is one of them. Similarly, epsilon wall functions and nu t. So for the cylinder head also these are same. And the last boundary condition is alpha T. So alpha T is the turbulent thermal diffusivity. So how temperature is diffused by turbulent. So this value represent that those property. So alpha T it is located inside case settings wall alpha T. So if we go at boundary conditions and alpha T, so this is the way it. So actually alpha T is calculated from nu T. So if we divide nu T divide by the density times the Prandtl number, so we can get the alpha T value. So there is a relation between relation for alpha T and nu T. So we can calculate from the nu T or the eddy viscosity itself. So and the effective viscosity is the sum of nu T and the molecular viscosity. So these are the boundary conditions, and this boundary condition we will use in our entire all the cases. So we won't change the boundary conditions for these files. So note that the file is air. So we need to include, if you want to model reaction, then we need to include different other species file. So now let's go to the reacting form tutorial. So this is also tutorial case of reacting form. So inside reacting form, there are different type of based on the turbulence model. So if it is laminar, RAS, and Lagrangian. So let's look at the laminar model. So this laminar model. And please note that we will be using a laminar model for our combustion simulation. So we won't be moving. So you can also choose the other turbulent model. So there are turbulent model also available in the tutorial cases. So you can just choose a turbulent model also. But for our simplicity, so we'll be sticking to the laminar model for this demonstration. So what we will do is we will copy these files CH4, CO2, H2O, N2O2 into our cold engine form file in the cold engine form folder or directory, and then we'll modify it in that directory. So similarly for the chemistry properties, combustion properties, and these files we'll copying into the cold engine form, and let me show. So after I copied it to the folder, structure would look like this. So here I've already copied in the cold engine form. So CH4, CO2, H2O, and to these files, this species files are I've already copied and placed it in the cold engine form file. But why have I placed it here? Because I have already said that this cold engine form do not solve for the scalar transport equation. But what is the use of using it then here? So why have I used it here? Because because the properties of air and the properties of these species will be different. So instead of in thermophysical properties, instead of using properties of air, which the cold engine form uses, so I have included the thermophysical properties of the compressible gas. So while so now the cold engine form also becomes it do not use the air mixer, but it uses the specific component mixer. So now if I have to include this component mixer thermophysical properties in my simulation, then I have to include these files also. in the zero folder, or also have to provide the boundary conditions for this file. So if I don't paste it here, or if I don't use these files here, and simply I use here or the boundary condition for here, then this will throw an error. So that is why I have placed these files here and have assigned the concentration also. So actually this concentration will not change. This concentration will not be calculated, anything that sort of things will not happen, but just for the but this is required for our simulation to run. This is because the structure of the OpenFOAM solver, OpenFOAM case is aligned in that way. So just to match the structure, we are copying it here. So you can run the tutorial cases, but I will not run it now, the tutorial cases. So I have here a reacting foam. So this I have already. Let me first run the case, and then we can talk about that. So first, let me run block mesh. So these in the non-uniform. So we can see that there is a file called engine mesh, engine geometry. So this engine geometry is the actual dynamic meshing library available for cold engine form. So it uses a layered mesh approach, and the engine type is free piston. So and free piston, this free piston to use this boundary condition, we need to provide piston position timetable. So this is required for the to use free piston. So if you go to your I think it's located in solvers. Which is actually SRC. So engine. So you can see that there is the library for the free piston. If you go inside the .c file, so it will ask for, so it will say look up for the piston position time. So we need to insert piston position time if you want to use free piston. So this so in this way you can check what type of inputs have to be required required in that object file. So how can we know that what is required to be inputted? So you can look at the C file and you can see what it is what the C files ask for. So piston position timetable. So I provided these time in the form of table. So at zero second, it is at this is the displacement magnitude. So the actual length is 0.1. So at 0 second, if you look at our paraform. So if you look at our geometry at 0 second, this is the displacement magnitude is 0.1, the distance magnitude is 0.13. Now as we compress, as the piston moves, then at 0.02 second, it has to become 0.013. So it has the magnitude has to decrease. So it will, I think it will reach somewhere 0.13. So if you look at that, so it will reach 0.01. So distance between this will be 0.013. Now it is 0.13. The magnitude is 0.13. But after 0.02 second, the magnitude or the length would be 0.013. So this so this table is saying that those things. So at 0 second and all these. So this is actually defining the parameters of our mesh movement or the geometry piston movement. Okay, now Okay, so now another also important file is the set field stick. So what we'll do is we'll at first assign the half of the cell with CS for 1 and another half of the domain with CS for 0 and only oxygen and nitrogen, and the default species another default part will be assigning with nitrogen 1. So also one thing to note is that species that the mass fraction should sum up to 1. So 0.23 plus 0.77 it should be equal to 1. So here it is also 1, another part is 0. So let me first run the field strict. So I have in the state fields. Now let me check in paraform. Set fields, let me see. So after we run set fields, so it should be the internal field should be initialized with different values of the CS4 species, CO2 species. So we have as we have defined in the set field stick. So I can see that the variables of CS4 is not present here. So we run just paraform. So yeah, now it's showing the fields. So let's turn on all these fields. So yeah, what I was doing, I'm setting up my domain with this part with CS4, and after that, and this part with oxygen, and the remaining part that is the remaining domain with nitrogen. So in this part, there is nitrogen as well as oxygen. So there is so this color is different. So by the set field stick, we can initialize our domain or internal field with different values of scalar concentration of species concentration. So this is what I was what set fields did do. So now the other thing I've explained the geometry, the dynamic mesh, how the mesh moves. So momentum transport it is already explained. And thermophysical properties, let's look at thermophysical properties. So it uses HEP as a thermoclass. So and it uses the multi-component mixer. The different component we can assign, like the species we can assign using this mixer model. And the transport model is other than model, that is it computes the viscosity and diffusivity based on the change in temperature. So it is very useful for the combustion simulation, since the temperature will rise and it will change. And the thermo model that is to calculate the coefficient of specific gas constant, specific gas constants. Then we need to we use GNF polynomials. And for the energy equation, we use the sensible internal energy. There are two available, that is sensible internal energy, and we can also use the sensible enthalpy. But for the piston simulation, which is a closed system, we can use a sensible internal energy, because the piston work will be used to build the will be used to increase the internal energy. And the equation of state is perfect gas, and species is species class. So default species is N2, and we have included a file called thermal compressible gas. So if you look at thermal compressible gas, this is the file. So here we have assigned different species: O2, H2O, CH2, CO2, N2, and for all the species, these are their parameters. So the transport ASTS. So this is actually Sutherland. The constant that are used in the Sutherland model. So it calculates the viscosity and diffusivities values based on these constants, and this is the TNF table. So the operating range is from T200 to 5000, and this is the common temperature. So if the temperature is below 2000, below 1000, then it will use the low CP coefficient. So these coefficient that I had shown, so these are the coefficient of this equation. So A1, A2, A3, A4, A5, A6, A7. So actually we get a 7 coefficient. So these are inputted in that polynomials. And below this common temperature, we use the low CP coefficient, and for the higher temperature, we use the higher CP coefficient to calculate CP. And molecular weight is this is the molecular weight of the gas. And so all the physical properties, thermal properties of the species or the reactants are defined in the thermodot-compressible gas. Okay, now let's run the simulation now. Stroke. So we have run block mesh, we have run set fields, so we have already run that. Now we can just run our solver. So our solver is cold engine form. So while it runs, we can see other things also if I have missed anything. So let's look at control dict. So control dict, we have used the cold engine form, and the time step, we have used the delta dBs 5 - 7, and we have added to time step. So it will adapt the time step according to the maximum current number 0.25. Because in the dynamic mesh simulation, the mesh cell will decrease, like it will get compressed, and the mesh size will decrease, the del X will decrease. So when del X will decrease, then that will tend to increase the current number. So we need to monitor the current number and decrease the del T accordingly. So that will be done by adaptive that address time step. So I now I'm at time 0.021. So our simulation is completed. Now let's visualize the result in ParaView. So for this demonstration, we'll only visualize or we see the result qualitatively. We won't be looking at the quantitative results. Terraform. So let's look at the species. Let's look at CSPO. So this we are not using cold engine form and I have already said that this will not solve for the species transport. So if we run the Simpsons, so we can see that the species is not mixing or is not spreading anywhere, because we are not solving for the velocity is not able to spread or advect this scalar, because we are not solving the scalar transport equation. So this was one of the drawback of the cold engine form. So if you want to simulate the, like if you want to compress and the gas and we want to mix, we want to see the mixing or spreading of that gas, then cold engine form will we can do that. We can't do with the cold engine form. Similarly for O2. The other fields are properly captured, like the U. So velocity will be captured, and temperature will be captured. But we can notice that these because the spread is not happening, that diffusion or the spreading is or movement of this scale is not happening. So the temperature, and we can also notice that the place the internal field where there is CS4, the temperature rise is quite less than with other than the parts with other gases. So the CS4 part, we can see temperature rise is quite low, because this is based on because based on the adiabatic relation. So T2 by T1 equals to P2 by P1 to the power gamma minus 1 by gamma. So the gamma for CS4 is less than that of air. So that might be the reason why the temperature in the CS4 part is less than the other part. So this is one of the drawback that the cold engine form poses. So we cannot model the scalar transport, but we can model the properties of the like if we had used an air mixer instead of these CS4, all these species. If we had just used air mixer, then the temperature profile would be different. Temperature would the temperature now it has reached 810 because we have used different species. But if we had used air mixer, then the rising temperature or the maximum temperature would not be the same. It would be different. So thermophysical properties we have included in the cold engine form solver. That is a good part. So but we are not able to calculate the scalar transport. Now what we can do is we can map these final time state data to reacting form. So as we have compressed the piston, the temperature will rise. The temperature, pressure, it will be calculated by the cold engine form. Now we can map this to the reacting form solver as the initial condition to the reacting form solver. So the final state of this can be mapped to the initial state of the reacting form solver, and we can solve the diffusion, like the advection, all those things in the reacting form solver, because that includes the Y equation. And we can also model combustion, because reacting form will also be able to model combustion, but cold engine form is not able to model scalar transport, is not able to model the reaction also. So the next step we will be doing is we will map this in the reacting form. So this is another folder where I have the reacting form solver and the case setup for the reacting form solver. So let's open a terminal here. So WSL, and let's source the open from version 9. Now, first of all, I need to run the block mesh. Now, before mapping, we need to make sure that the final state mesh, like this is the final state. I think I've already closed that. So this is the final state, the final mesh of the last time step of the cold engine form. So this mesh should also be present in the first time step of the reacting form. So if you want to map it, so what I mean is, so if I increase it, so this is my reacting form solver. for the power stroke. So in the cold engine, in the previous simulation, we have simulated the compression stroke using cold engine form. Now this is the we are going to simulate the power stroke. Now if you see at the mesh, so you can see that I have made the mesh such that it matches the final state of the previous case, so that I can map all those fields field data to this reacting form, to this initial to the initial as initial condition for the reacting form solver. But in order to map, we have a command called map fields consistent. So consistent mapping will be done, and we need to provide the source time, and source time will be the latest time of the previous solver, previous case, and where it is present. So it is present in the cold engine form monitoring. So we are mapping. So you can see that what I am doing is from this to the case that I have run previously. So I am trying to copy this file of the last time step to the initial condition to these another solver that I'm going to run. So here we have see that there is no zero folder. Now after I run this command, so you can see that I have a zero folder created here. And what the zero folder consists of? So it consists of the latest time fields of the previous solver. So if you open this, okay, if you open U, because we have not solved for the U, right? But we can see that U has been mapped here. So this is called map. This is done using map fields. Now for the reacting form solver, there are different. We need to model combustion phenomenon here, and I have already said that the reacting form solver cannot incorporate engine mesh, and dynamic mesh by dynamic. You cannot move using engine mesh. So we need to specify the mesh movement using dynamic mesh dict. And let's go one by one. So let's look at the combustion properties first. So I have said that we are modeling laminar combustion model. We can change this turbulent based on the tutorial cases that is also available for RAS models. And let's look at the thermal properties. So the thermal properties file will be the same that I have already explained. Now let's look at the reaction. So this is the actual reaction. So this is the reaction that is taking place, and type is irreversible Arrhenius reaction. So Arrhenius reaction. So this is the to calculate the kinetic rate coefficient K. So this formula can be used, and we need to provide the constant values, like the A is provided, and beta is provided, and TA is provided. The TA, I think TA refers to the ratio of activation energy by R or something like that. So we need to solve for so RNS reaction. This will provide the kinetic rate coefficient based on temperature. So you can see that with the local temperature T, these K will vary. Now as the K will vary, so this is very important part. Okay. So as K varies, so K means rate of reaction. So the rate of reaction varies, so this will also affect the further reaction. So how do we solve this? How do we solve the rate of the chemical reaction is defined in the chemistry properties file. So the chemistry for the chemistry part, to solve the chemical equation, not chemical equation, the chemistry differential equation. So basically the chemical differential equation would be if S is the scalar, then ds by dt equals to minus k times S. So actually we have in the previous session, yesterday's session, unsolvable modification. I think you had seen how we have modeled how we have modeled the change of the scalar using minus ks. So ds by dt equals to minus ks. But we do not directly provide minus ks as a source term to our scalar transport equation. So if we do not directly provide as minus ks to our source term to our scalar transport equation, but we solve that ds by dt using integration techniques, and the value that we get, then only we will add, then only we will provide add a source term to our scalar transport equation. So so that is why these how to solve that, how to solve this ds by dt over the time. So this solving method, numerical method, we will specify in the chemistry properties. So you can see that it is using a solver called chemistry type solver is used or implicit. So you can go detailedly into these solvers, like how do they solve that scalar change reaction. And we need to if you do this to none, then this will turn off the chemical reaction. So you should make sure that this is on if you want to simulate the chemical reaction part. And this time step is for that. This is not the flow time step. This is time step to solve that ds by dt. When we integrate, so we use this small time step. So we need to use smaller time step to solve these type of reactions. And also, we should note that the K will also change based on temperature. So we have included reactions here. So reaction, this is also this can be accessed by the chemistry properties in the chemical properties dictionary itself. So this is how the chemistry is modeled. So because when the reaction happens, then the temperature will rise, because it will release heat in the system. So when the heat is released, then K is also sensitive to increasing temperature, because it depends upon the temperature. So K will also rise. And now when K will rise, the rate of reaction will be faster. So this will again tend to increase the temperature. If the reaction is faster, then the product formation is more. So the heat generation will also start to increase. Now, again, the heat generation will trigger the rise of K. So this is a loop. This acts as a loop. So this loop should be modeled, and this is already modeled inside OpenTune. We don't need to model these things. This is already available in the solver solver modeling itself. And now the last file for the for the moving boundary is the dynamic mesh dict. So this is dynamic mesh dict. So we have used, as I've already showed in my presentation. So we need to solve a displacement Laplace equation. So in this way if we can solve for the mesh velocity. So, and diffusivity value is uniform 5. So diffusivity value. So this lambda, this value is we have assigned is add uniform 5. So this becomes a differential equation, and we can solve the differential equation using FVM techniques, and we can find the mesh velocity. Now another file that if you want to use dynamic mesh, another file that is important is the point displacement file. So we need to specify how the boundary will move. So we need to specify the boundary conditions for all the boundaries. So we can see that since our cylinder head is static, it doesn't move. So we have provided 0, 0, 0. So it won't move. Now piston, which is a moving boundary. So we have provided an oscillating displacement. This is the magnitude, and this is the magnitude. This is the amplitude, and this is the omega. So omega, that means angular frequency. So if this equation y equals to a sine omega t, so we will model the movement of that boundary using sinusoidal motion equation. And y minus 0.5, 0.1 minus, because we are going to expand our mesh. So in the minus z direction. So if you look, so this is the plus z direction, and minus z is downward movement. So we have already compressed in the first case. We have already compressed to positive z direction. Now we want to expand our mesh, so it should be negative z direction. So that's why the negative value is provided here. And omega, this is the angular frequency. So how fast do you want to how fast do you want to move? Do you want to move your boundary? So if omega is high, then time period will be less, because 2 pi by omega equals to t. So if time period is less, then the moving boundary will tend to move faster. So in this file we need to provide the movement of the boundary condition for the moving boundaries and all the other boundaries also. And also one another thing important is liner we have assigned is as type 0 gradient. Why? Because the liner also moves along with the piston. So these should be calculated. So the boundary condition liner should be calculated based on piston. So we cannot assume it at fixed value, because the liner is also moving. So zero gradient means this is calculated based on the nearby cell value. So we do not assign any fixed value to the liner, but as the piston moves, the movement of the piston is transferred to the nearby cells, to the liner also. So it will extract that cell value, or that mesh velocity, or that displacement value, and we provide it to the liner also. So this basically means the liner moves along with the piston, but cylinder head is static. Front and back we will keep it as wedge. Okay. So these are the files. Now let's see by running our simulation. So first let's create our mesh using block mesh. Now there is one important solver, or what important command called move dynamic mesh. So this move dynamic mesh, it do not solve for any fields of any other equations like the like momentum equation and the ns equation. This will only solve the shell displacement. This will only solve for the shell displacement. It will not solve for the velocity, pressure fields, but it will only solve for the shell displacement field. So if you run this, what it is saying is cannot find file 0 in the. So if you look at 0, so please note that we need to provide boundary condition in the 0 file, not at 0 original. So 0 original, this is why I have here 0 original, because whenever I run set fields, so set fields will change the boundary conditions of 0 file. So it is always recommended to keep the original file at 0.org. But we can see terminal that it is saying that this point displacement file is missing, because there is no mention of point displacement. So let's copy that from the 0 original to our 0 folder. Now let's run the simulation. So let's remove dynamic mesh. So now see, you can see the mesh is moving. So let's run for some time. Let's because we need to run other simulations, other cases also. So let's stop the simulation. Now let's visualize it in ParaView. I think I have so the time step is very less, so it is not writing any file. So let's first change the time step to a smaller time step, so that just for the dynamic mesh movement, so we can just decrease this to around 5 minutes. We will later increase while solving for the other fields, but for the dynamic mesh, we'll decrease that for to see the mesh fast. Move dynamic mesh. So this is the command. So see now is files have generated. So let's visualize in ParaView. So you can see that piston is expanding now. So previously piston was compressing, now piston is expanding. And we can see cell displacement. So we can see that the displacement will be concentrated towards the moving boundary. So you can see this. So if you want to visualize within surface with edges, so you can see that the deformation will be concentrated to a specific region. But let me show the previous case when I had used the layered mesh approach, like the engine mesh approach. So this is the part. So this is with the engine mesh layered approach, not with the dynamic mesh dynamic mesh moment. So what we can notice is that every cell moves with the same deformation. So, but we cannot see cell displacement here because this is not calculated. It is only calculated in the using the dynamic mesh approach, the dynamic mesh library approach, that is the displacement Laplacian approaches. But layered approach, what it does is it will deform every message equally. So it won't like discriminate between these meshes. So diffusion is equal everywhere. Diffusion of the deformation is equal everywhere. So we cannot achieve this using we are not able to achieve this using the displacement Laplacian approaches. So even if we set different diffusivity values and everything we do, so see if you go at the dynamic mesh dict, so even if we change this to uniform 5 to inverse distance diffusivity type to diffusivity type to the inverse distance or uniform 10 uniform 0.1, so we cannot actually achieve what this engine mesh is doing. So it is actually deforming every cells equally. So that is why we this type of dynamic.
Hello. Yeah,
Yes,
sorry,
ma'am.
Manjil, I'm just interrupting. Actually, the online attendance form has been put in the chat box. So can we wait for 1 or 2 minutes and then you can continue?
Okay, ma'am.
Yeah, okay. So participants, please fill up the attendance form and then we can continue.
Mansil, most of them I think done because they are putting a thumbs up in the chat. Okay. So you can continue.
Okay, ma'am. Okay, so I was talking about how the diffusion of the deformation will take place in this type of dynamic mesh mesh movement. Defined use so the where the mesh velocity or mesh displacement is calculated using by solving the Laplace equation. So the uniform, it is not uniform. Even if we assign it as uniform 5 or uniform 1, so this will discriminate between different regions. So we don't want that because if we like compress it further, so we'll see like how this type of morphing mesh strategy will fail if the displacement is very large. So right, I think this time I have shown how this type of how the diffusion works between the layered mesh, like engine mesh approach, and the uh, this displacement Laplacian approach. So let me close this now. So I had solved just for the moving mesh, move dynamic mesh. So now we need to solve for the solver also. So let's first clean the tutorial. So this is the command to clean the case. If you just do this, then the case will be be cleaned itself. So now there is no any timestamp data. Now let's run block mesh for creating our mesh. Then set fields. But we don't need to we don't need to run set fields, because what we have done is if we run set fields, then this will again change this CS4, this internal field to other values. But we don't want that, because we have mapped this data from the previous solver of cold engine form. So we don't run set fields here. If you run set fields, then this CS4 concentration will change in the overall domain. It will reset itself to that we had defined in the set fields dict. So we don't want that. So this will reset itself. If you run set fields, then this will be initialized instead of the mapping that we had done. That will be of no use. So let's just run the solver. So the solver is now reacting form. Now what things we need to observe after we run reacting form. So we know that reacting form, it solves for the scalar transport equation also, and we have also modeled the combustion. So we have turned on the chemical reaction part also. So we need to see the formation of CO2 and H2 also in our results. So let's see if these are how CS4 and CO2 is formulated. And we'll only look at the qualitative results in ParaView. The quantitative results you can later on work on that, on the quantitative parts. So let me open a terminal and launch Paraform. So this was from the previous case. So this we had mapped. So if you look at 0.003, so let's now run the simulation. So we can see that the piston is expanding, and let's see the formation of other gases. So we can see that CO2 is starting to form with the ratio of 0. something, so 0.14 CO2. So in this way, so CO2 has started to form, and we can also observe S2O should also form. So S2O is also forming as the piston expands. So as the piston expands, the velocity is also present. So you can see that this velocity will convect or advect the scalar, that is the concentration, and it will also diffuse on itself, but it will also be advected by the velocity. So we can see that in this point there is high velocity. So this is the point where this is the place where the carbon dioxide, these react products are shifting. So you can see that it is moving towards high velocity. Yeah, so that's Now you can also see the temperature. So temperature has reached 22,300, and I think we had set up this so the simulation. So why is this excessive rise in temperature happening? Because I think we have initialized the internal field with maximum temperature 700 at 35. Okay, no, it's not. So that's okay. So actually, the product is forming, and this will also the product formation will also cause an exothermic reaction, and the temperature will tend to increase. But I want to make sure that we had set up with the internal field as the so internal field T. Okay, so internal field was set up with 350 Kelvin. So what happened was while compressing, the temperature will increase. The compression at the compression stroke would tend the compression stroke from the previous cold engine form. It increased the temperature, and but the product was not forming at that time. So after that, we simulated the combustion using reacting form. So now the product is forming. So why the product formation is also more, because the temperature was very high while we had compressed. So if the temperature is high, then the rate of reaction will also increase. So so we can see that the CO2 concentration is also quite more 0.14. But if we had compressed less, or only done half compression, or some only a bit we compress, then this CO2 this ratio of CO2 would not be formed. So this is due to the compression stroke being very much lower to the top dead center, that is seen in the red. That led to the high temperature, and the high temperature had led to the formation of more CO2 and H2O. So let's approach this now. Now let's look at the next case. Okay, we have looked at the next. Now the another case. So let's look at the third case. I think let's look at presentation first. So we have simulated cold engine tutorial case. We have simulated reacting form tutorial case. We have simulated cold engine form plus reacting form by mapping all these things. Now let's use only reacting form solver to solve this case, both the compression and power stroke. Just only reacting form. Well, let's solve this first, because we have, I think, 30 minutes remaining now. Okay, so reacting form, compression and power stroke. So this is the file. So just you need to change only one thing. So just you need to change the point displacement file. If you look at the point displacement file, we need to compress and expand. So what we do is the amplitude is 0.05. So we compress first to positive z direction. So again, I will show this. So we move to 0.05 up to here. So if you look at this geometry, from 0 to 0.05, we move here. That is the amplitude, and this is the amplitude, and after that it returns back to the mean position, right? So it moves up to that amplitude, and then it returns back to the mean position, and it expands in another direction to amplitude of 0.05. So in this way, this will simulate, and the omega is 10. So this time period is very fast. So the simulation will run very fast, because we also have less time. So we need to, and the piston movement is also, I think, quite fast. So this is these parameters I have chosen it arbitrarily. You can also like it depending upon the like RPM and everything. So I think we need to assign these values, but just for this case demonstration, I have chosen any arbitrary value. Okay, so let's simulate this first. So let's just move. So let's not solve for other for the whole fields. Let's just solve dynamic mesh movement first, like we had done. So first, let's create file. Let's see a time step. Let's reduce it. So 1 minus 3. So while solving dynamic mesh, we can increase the time step. But when we solve for the for the other fields that the solver itself, then we need to increase the time step again, because that might lead to divergence. Okay, let's launch this in ParaView. Now let's see the movement. Now we can see that the cell displacement again. So the displacement of cell is concentrated towards the moving boundary, unlike in the layered approach. The dynamic mesh, in the dynamic, if you want to define the mesh motion using dynamic mesh, then this is kind of a limitation for large displacing boundaries. So you can see that this is moving further up and down.
Manjil, there is a question in the chat box. You can take it now, or maybe we can address it later also.
Yeah, I think you can take it at the end of the session.
Yes, yes. Okay, so Evan has replied to me.
Okay, now let's see the limitation that comes with this morphing mesh. So let's first clean this tutorial. Home clean tutorial. This is the command to clean the case. This is clean the case. Yes, clean. Now let's say that we want to compress it more. Like we are only compressed 0.05, that like it's less than half compression. If you want to compress 0.1, so nearly to the to the top dead center or the cylinder head. If you want to compress to a further extent, so let's now run run using this. So let's run block mesh. Dynamic mesh. So we can see that we are getting the errors at the we can see that failed mesh check, failed 1 mesh checks, failed 5 mesh geometry checks. So the mesh has failed. So how it has failed? Let's look in paraform. So let's see. So you can see that the mesh has completely distorted. So even changing, just we increase the amplitude of our moving boundary. Now this cannot, this morphing mesh cannot simulate such high amplitude boundaries. So this will fail. Even if you try different approaches, like if you change that diffusivity values to uniform or inverse distance, which you can try, but it is still very hard to simulate for a large displacement boundary using morphing mesh. There are other approaches like the AMR, but the best approach that we are already used is the engine mesh, which is a layered approach. So for that, using that engine mesh layered approach, we can simulate a very high displacement boundaries, and which is particularly designed for the piston IC simulation, engine simulation. So this is the drawbacks that I wanted to show for the morphing mesh. So we can simulate for that. So let's clean this case first. And set that value back to let's say 0.05. And now let's run block mesh. Now this is our case with both compression and power stroke. So we will compress and the power stroke and compression and power stroke is both done using reacting form. So we have not mapped any data from the previous run cases. So we can just do set fields here. So now if you look at paraform, so set fields, it is the same with the previous case. So this is the CS4, and this is the half other internal field is. So you can also like you uniformly define the field. So in the here I have only defined CS4 in this part of domain. But you can, but this is not like the real case, because this will not be concentrated at this part, and the O2 will concentrate at this part, but this will already be mixed together, right, in the actual piston. Or we will have different inlets. So the spray modeling is not done here. So this is a very basic basic demonstration to show how the reaction will take place at the interface. So we can see that the CO2 is also forming at the interface part only, where the CS4 and CO oxygen come in contact. So other part it won't be formed. It won't lead to the formation of CO2 and the product. So this is O2, and now let's run our case. So let's run reacting form. Now this will solve for the reaction part also. Now, previously we have only solved for the cell displacement. Now this is solving for the solver. We are using the whole reacting form solver itself to solve for all these fields. So we can see that the fields are generated. Now next case we will be running is how does the if we set the internal field temperature to around let's say uniform let's say 2000 value. So now I have now in the next case that I will be running will be setting up with uniform 2000. So previous cases the temperature was 300 350 I guess. I think so it was with 350. So now if we increase the temperature internal field temperature like the Ortistat previous Ortistat type of condition, then what will be the difference? So let's see that. So let's also run this case. So everything is same from the previous case. So this case and this case, the compression and power ratio that I had just shown is same, but I have only increased the temperature in this case, the internal field temperature. This command are the same. So let's visualize these two cases together in ParaView. But I forgot to change the time step in control depth. So it is kept -3, but the simulation is not diverging, so it's fine. but we could have decreased this delta T. So now let's close this also. Let me open both these cases in Paraform. So we are not we are not visualizing, like we are only focusing on the species part. So temperature now let's see. This is the case with the high temperature, right? So the temperature is 2600 here, and let's see the another case. So your temperature is 360. So the temperature is just 360 degree in this case, or 420, let's say. Now let's see the formation of CO2. So we can see that CO2 formation is very, very less, 8.1 E minus 7. So, but while I had increased the internal field temperature, so we can see that the CSO formation, CO2 formation is larger. Let's say 0.04, and it increases as we move compress down. So you can see that CO2 formation is greater because just we increase the internal field temperature. So this formation is sensitive to temperature, because the equation itself says that. But these two aspects I wanted to show for different T internal field. So why is the temperature less? Because we have not we have not compressed it so much higher than the previous than while we had done with using engine waves. While you had used cold engine foam and mapped that to reacting foam, the cold engine foam had compressed the cylinder heavily, like to the near to the cylinder head, so that had resulted to more compression and more in the rise in temperature. But the reacting foam using dynamic mesh it cannot compress the cylinder to a large displacement, so we cannot expect the heavier rise in temperature. So that's why the temperature is also less and the function of CO2 is also less. So this is quite unrealistic, not unrealistic, but we cannot reach to the extent that the cold engine foam or the engine mesh delivers. Okay, so I think we are now left with the last case. So the last case is engine foam. So this is a compact solver that is available in OpenFOAM. And this engine foam, this solver has all the capabilities that were missing in the previous solvers, or that were not present in previous solvers. So engine foam, so the cold engine foam, it did not have the scalar transport equation. So it did not, it could not solve the chemical reaction, chemical reaction part. And but the reacting foam, it solved the chemical reaction part, but it could not incorporate engine mesh in engine mesh file or the engine mesh object in its setup. So that resulted to less that resulted to we could not achieve more heavy displacement using reacting foam. Now there is the another solver which is also a part of engine foam, or we can say in reacting engine foam. So the tutorials are not available, I think, for this engine foam case, but there is a solver for engine foam. and this will simulate. So I have already run the case. We do not need to run the case again. So this is the same. The setup is same. So nothing is different here. But the difference between the reacting foam and engine foam is it is same, but we can incorporate engine mesh library or engine. We can incorporate the movement of boundary using engine mesh, engine geometry. So you can see that this is the engine geometry object. Inside the object, so I have not used dynamic mesh dict here. So the difference between the engine foam and reacting foam is highlighted here, which can use engine geometry. So if we can use engine geometry and or the layered mesh approach, and we can also simulate the scalar transport, and we can also simulate the commotion phenomenon, then this makes a compact solver. So this is what this is already, and this is already this is solver that is already present in the open form. So the case is already the case has been already run. So if you look at the piston movement, so now we can see that I have included four different time step and four different position. So at 0 it will be at 0.13. So this was the previous case when we had compressed the ceiling piston. Now we want to expand it also. So this is for the expansion part. So 0.04 it will reach here, and 0.06 it will reach here. So this I think you can easily understand. So this is compression and this is expansion. Now let's look at the results. So we can see that we have we can reach to a further extent. Displacement we can easily displace the piston more than the previous case, which we cannot achieve using the dynamic mesh libraries present in the open form. So this layered mesh can allow us to achieve more heavy large deformation boundaries. So you can see that these CH4 similarly, let's see the CO2 formation. Let's see the CO2 formation. So we have run this for with very high amplitude and we have only stored the larger time, like the time step data. So if you want to visualize more clearly, you need to store that the less time, like we have stored the 0.001. You can also store data difference with 0.0001. So this will also or you can also decrease the the motion of the boundary, like you can decrease the omega of the boundary also. So we can see that CH4 like the CH4 will be consumed while in the because the reaction is taking place because CO2 is also forming. So and we can see that it is moving. So here you can see that the velocity is advancing this scalar, because if you see at the velocity, so you can see that the velocity is very high, 6.5 magnitude. So this CO2 that is forming at the interface, it is being convected by the velocity towards the piston. So that's why this S2O CSO is moving accordingly with the velocity. And the temperature, let's see. So the temperature So let's see at the end of the compression state, what is that other temperature becomes. So we can see that it's 22 on no, yeah 2200. So because we have compressed it very much, so that is resulted to heavy temperature, and the temperature rising temperature itself triggers the reaction to accelerate faster, and this will again increase the temperature. So that's a kind of a loop. So you can also plot these things using so let's plot the scalar. Um, so what we can do is okay. So at this, let's see. Let's plot along a line. Mm. So actually, this should sum up to 1 in every cells. So if you add these values, then this should sum up to 1 in all the cells. So in this part, let's look at this part. So this is just a mirror of this graph. So CS4. So it is 0.6 here, and it is N2 is 0.4 here. So when we add this, and I think there is also some formation. There is also some O2. So if you add this, then this should equal to 1, because the mass conservation requires that even if it is converted to another product, then that product will have to fill that empty space. So we can see that these all add to 1. So you can also check that in the internal field itself. If you look at CS4, CO2, S2O, N2, and O2. So let's look at the latest time. So yeah, I think if we also check these internal field data, then and add these values of the at any time, this should also sum up to 1. So let's see at this first line 0.813, and so you can just check using calculator itself. 0.014 plus 0.813, 0.813 plus the formation of CO2 0.017, 0.017, CS4 is 0.154, 154, and O2 is some these values. So you can see that it is nearly equal to 1. So in all the cells, this has to be satisfied for the that the concentration should be equal to 1. Otherwise, so while setting up the internal fields also, we need to take this thing into consideration, so that the mass fraction should be equal to 1. So that's combustion case. I know this is a very simplified case of the piston cylinder, and we can have a more complicated and 3D cases, but the work but the setup would be the same, just geometry would be different, mesh would be different, and we need to take care of the different turbulent models. So small things have to be considered for a more result specific simulation, but this is just to show how we can achieve a simple piston or a simple compression and power stroke using the available solvers in open form. You can also modify the solvers on your own, or you can work around the solvers and create your own solver. Like you can also use AMR for the mesh refinement. So these because there is also always an open space for modifications, because this is the open form is a open source software, and anyone can anyone can learn, modify the solvers based on their problems and requirement. So that's all from my side. So thank you everyone. And you can ask me by unmuting yourself, or I'll also see if there are any queries in the chat box. So yes, thank you.
Yeah, there is a
Thank you
query
very
in
much.
the chat box. There is a question by Plavan Sen in the chat box.
Manzil, can you view the chat box?
Yeah, I'm seeing the chat box.
Okay. There is one question by Mr. Vivek and one by Plabin.
Can you explain this figure and what is profile for this species? Concentration profile. So you want me to explain the figure? So it is a simple single block, which is a wedge. Because in the wedge direction we do not solve. We don't want to solve in the wedge direction. So this is just for simplifying our case. But in the original 3D simulation, we might have to solve for all the 3 directions. So yeah, this is a simplified case. And the profile for this species. So these species are already provided in the tutorial cases. The thermophysical properties of this species are already available. And another thing you can check out is there is another reaction model. So let me show. So you can see that I have only used this a reaction model that is a simple and a single reaction. So this, if you see at the reactions file, we have used this single line of reaction, only one step reaction. But there is a model for the GRI MAC. So you can see that GRI, TDAC, 2D LTS. So you can, if you look at these files, there are a series chains of reaction. So you can also incorporate all these in your case setup. So these are the so these reactions can be used for your problem also, if it is required. GRI MAC and other types of. So you need to I think yeah. So what are the things you need to change? You just need to include this reaction, and after that thermophysical properties. So you need to include these all these species and on their properties in these thermodynamical gas GRI. And after that, I think we can run like the previous cases. So if that you are asking if by the profile for this species. So I think there are other software tools like Cantera also, which provide provide the data for all these species. Single step combustion and multi-step. Yeah, multi-step combustion can also be achieved. We have only done the single step reaction here. So I think this solves your queries, or is that what you have asked, or is it like different question?
Hello.
Hello?
Actually, my question was like in the graph you have shown methane. I mean, for example, suppose you take methane or some other species, the dynamic behavior that is shown, it is increasing and decreasing, again further increasing. That I mean, why this kind of behavior? I just wanted to understand.
I think that might be due to due to the what we call dynamic mass movement. So the concentration will it won't be equal one, because when we compress the mesh, the some part of the CS4 might leak out of that cell to another cell. So but the concentration should be equal to one. So that is filled by uh, other gases like O2 and N2, the default species gases. So this behavior might be due to the mesh compression. So the concentration is it is being distributed to other parts. So you need to know exact. We need to work more on the quantitative results part, like why is this happening and why this is changing. So that's why I was only trying to show the qualitative results. But yes, you need to work around with these quantitative results also. So why this phenomenon, why these values are occurring. So any other queries? Yes, CFL is related to your minimum cell size and delta T. So if you have any other queries, then you can also unmute and ask. So if I have a proper knowledge, then I can answer that.
Okay, so does anyone have any questions regarding Manzil's session or the session in the morning that was conducted by Nikhil? So you can ask us now, because we have a Q&A session until 5:30. So it doesn't necessarily have to be only from these sessions. If you have some query about OpenFOAM, or if you want to try something new and you are not sure where to start, but you can ask those questions as well. So we're still here. You can ask us and we may try to help you out. Okay.
Hello.
Yes.
Thank you for the lecture. I want to know if we can have access to the videos, the recording.
Okay, so have you registered for the whole workshop?
Yes, I registered, but
Okay.
yesterday I didn't sign attendance because I was watching YouTube.
Okay. So you can drop
Yeah,
us
so I
an
just mentioned this problem in chat box also. I have requested Kayo to please contact us via our email ID. We will definitely help you.
Okay.
Okay, so if you missed joining the session via Zoom and you have joined via YouTube and you have missed your attendance, please let us know through the email ID that we have provided.
Okay. So should I send you an email to state that, or
If you please email us about the issues that you have missed to mark yourself present yesterday, and we will take care.
okay? Thank you.
and the recordings will be shared via email, and after a few weeks you will be able to see it on YouTube also, so you don't have to really worry about the recordings itself.
Okay. Thank you.
Okay.
I'll just share the recordings that we have till, of the yesterday's session. So you can please download it and keep it with yourself because it's a temporary thing. So that link is a temporary thing that will be exhausted after say a period of 1 month. So it's better you can download it right now and keep it with you. I'll just paste it.
Did you send the link to our mail or here? The link to download it.
I am just pasting it here. I'll just paste it here in the chat
Okay.
box. In through email also we will give you after the workshop. After the all 4 days of the workshop, we'll give you.
Okay.
At present, we are sharing the yesterday's picture, Zoom recording.
Okay. Thank you.
I have also shared the YouTube link in which our sessions are being live streamed. So that will be there. Any other queries are welcome, as just Evan mentioned that if you have any questions from the morning session or today's session or anything related to, basic information about OpenFOAM. So our team members are here, they'll try to help you.
Yeah, so there is one question by Sibo. So if you want to differentiate between the .com version and the .org version, in simple terms is that the .com version you will have a new update or at least a new version after every six months. It's more like people are there who are developing that particular part, whereas the .org version is a bit lagging behind, you can say. You won't find all the possible solvers like the latest one or something that you are trying to solve or some stable solvers. So that's why we always tell you to install both .org and .com versions. So if you see the OpenFOAM 9 is a .org one and your OpenFOAM 2412 is the .com version. So you can then choose between which one you want to exactly use depending on the case that you're solving. So if you like for compressible cases, especially, you have more stable solvers in the .com version compared to the .org version. So we really prefer the .com over .org for those kind of cases. Whereas in some cases, if you're just starting to learn OpenFOAM, we would recommend starting with OpenFOAM 9 because the file structure and everything is quite simple and everything is segregated out perfectly. In the later versions, everything is clubbed up together, so it becomes a bit confusing. So if you're just starting off with OpenFOAM, go with openfoam.org versions. And if you are well versed in OpenFOAM itself, then you can go with .com version. Okay.
I have a question.
Yes.
It appears most of the cases we are solving from the tutorial.
The cases that we've
Uh,
demonstrated today and yesterday weren't particularly from the tutorials itself. We have our own FOSSEE repository. Basically, what we've done is all our previous interns who are there, like you have the summer fellowship, then you have the summer internship and all of those. So the interns, once they complete their internship, we upload all their files into that repository. So you have these files with their whole report, case files, everything. So you can refer to that if you are trying to do something similar and you just want to modify something. So you don't have to really start from scratch.
okay, if I understand you correctly, you will send us the file.
The files are already available. Like if I can share you the link, you can go on our website and you can see on the left hand side. If you want, I'll share my screen. Wait.
Okay.
Deepak sir, could you give me access to share my screen?
Given.
Okay, thank you. Okay. So let's say we open. So you can go to FOSSEE CFD. So we'll share this link in the chat. So on the left hand side, you can create your account first. Now, if you don't have an account, you can always see on the left hand side, we have the case study project and we have a research migration project. So under case study, you can click it and you can go to completed case studies. So over here in completed case studies, we have all the previous work that the interns have done with their whole detailed report, their case files, every single thing. It also mentions which solver they're using. So based on the solver, we segregated out things. So you can download these files and you can run it on your system itself. Just check which version they're using. Usually, if they're using anything above OpenFOAM 9, you can just run it on OpenFOAM 9. And anything, if they're using 2412, you can run that fine. Most of the old cases, like if you go down to around like 90 or 70, the 70th case study or the 90th one, those are a bit old. They are on OpenFOAM 7 or 6. So those cases, we are actively upgrading those. So after a certain time, you will have another tab over here that will allow you to download the upgraded case files. So that's still a work in progress, but the latest ones you can download them. So you can check them out. You have the case study also, and we have a research migration also. A research migration is just one particular step ahead of a case study. In this, you try to validate a pre-existing paper. So you can check in completed research migration. You can download any of these files. You can download them and you can run them on your own system. Okay.
Thank you very much.
Yeah.
Please, can you just send the link now?
Yes, I'll share it in a minute.
Thank you.
If there are no more questions, may we wind up the session for the day? You can just copy paste the link that everyone is sharing. And always we are reachable through the email ID that I just provided. So even after the workshop, if you have any queries regarding the case studies that are being demonstrated, you can just come back to us and we will be there to answer your queries.
Hello. Hello.
Yes, Mr. Mahesh.
Sir, actually, I have installed the OpenFOAM 9 and until 12.
Yes, Mr. Mahesh, you can speak.
My, I'm audible.
Yes, you're audible.
Yes, sir. I have installed both the OpenFOAM 9 and 2012,
Okay.
but my ParaView is not linked with the 2012. Only this is working fine with the OpenFOAM 9 version only. I have tried to you have given the commands and what's this is showing the error every time while I'm running a case after running the case and try to open that in ParaView.
Okay, so your ParaView is not opening completely.
Yes, it's showing error. I have to install it, which showing the error ParaView is already newer version is in there, uh, and nothing is opening. Nothing is open there.
Okay, so once your simulation is done, no, you
Yeah.
can type this additional command. I'll just share it in the chat box. You can type touch and then you can just add a file name, like
Okay.
whatever name you want to add, and you save it as touch file name dot foam. Okay. So like this, you can
Touch.
type this command and it will create a dot foam file in addition to all the run files that you already have. And then you can go on your Windows search and you can just type over the ParaView and open ParaView manually and then go to this file path, like whichever file you're trying to open, and open this dot foam file.
Okay.
Yeah, because if it's opening for OpenFOAM 9, you can still open it externally, but you'll have to load the file in manually.
So every time I have to be this command I have to use for that touch and file name and then.
Yes, because only then OpenFOAM, not OpenFOAM, but ParaView will be able to execute that particular foam file. If this dot foam file is not there, it won't really give you anything. You'll just have folders over there.
Okay.
Okay.
So can I install in between them? Because I try to install then and it's also showing an error regarding already the newer version of Paraform is there. When I try to use the sudo apt get install paraview commands also.
Yeah, sometimes whenever you install the whole OpenFOAM and everything, your ParaView might give you errors. It's very rare though. If you have done your installation properly, it does not really give an error, but sometimes it does give. So for those reasons, we tell people to try this touch.foam command because that is the only one in which you can really use the pre-existing paraview and all. Otherwise, you have to delete the paraview and manually install the whole thing separately. So if you don't want to do all that hassle, you can just type this touch.foam and you can go ahead with your whole simulation.
Okay.
Yeah.
Thank you.
Yeah.
Yeah,
And
the touch.foam works perfectly for me. Yes.
okay. And Mr. Mohit, you have asked a question regarding a demo, how we compare experimental data in quantitative data visualization in morning session. I'm not really sure. Like, do you want to compare your experimental data with some data that you are getting from a simulation? Is that your question?
Yes, sir. I need to check how the post processing and graph are representation for the experiments.
Okay, so now if you are plotting something, like if you're getting some data and you're opening it in ParaView, and like Manzil showed, you saw that there were some graphs and there was a like it was all over the place, right? So instead of generating that graph, you can also convert that into a .csv file, and then you can take that whole data set and you can put it in Excel or in any other software that you're comfortable plotting your that data with. So you can then keep one particular column with your analytical data and the other one with your simulation data, and then you can compare both of them in that particular graph on Excel itself. So that is one way you can do. The second way is you can write a custom Python code and you can again feed in the data and you can just plot the whole thing together. So are you aware of how are you supposed to extract that the graphical data into a .csv data from ParaView itself?
Yes, I know, sir. Last time I used to for the fellow internship screening, I do it for it.
Okay, okay.
Only thing new data are streaking, that's earlier morning class, the new experiment data are being given, but I don't know how to compare that data.
Okay. Manzil, are you there? Okay. Because I don't know exactly what
Yes,
Nikhil
Shivam.
has. Yeah, did Nikhil show some visual data or something while he was doing a session?
Actually, actually, I think he had only shown the
Nikhil
qualitative
was not there
results.
then. Paris was there.
Okay, okay. Okay. So see, ideally we try to extract the data using that .csv file only, and we just plot it in Excel if you want to compare any data. So that is the go-to approach if you're trying to just compare or validate something. So you can do that only. You don't need to do anything special as such.
Yeah, I can show that if you want to how to do that extract data
He knows how
in
to
this
extract
case.
the data part.
Okay, okay. So you want to compare with experimental data?
Yeah, he wanted to know whether Nikhil has compared it in a different way or something. I think Nikhil
Sir,
did it.
Nikhil sir not done. Arnav sir has showcased some research papers data.
Okay, okay. So Arnab sir, he might have his own data set and he must have compared that. But ideally, I'm saying that if you want to compare any data, you extract it into a CSV file and you plot it then with your data that you have.
I think we can also like extract data using digital plot, something there is software. So if you have graph of experimental data, then you can extract those data points also if you want to compare with your simulation data. Digital plot, I think plot something there is
Yeah, it is, I
to
think,
plot
digital
digitizer.
plotter. Yeah, yeah,
Plot
plot
digitizer.
digitizer.
Yeah,
Hmm.
something like that. If that is what you are asking.
Okay, sir. Thank you, sir. I noted down the steps and so what are the requirement. Whatever doubt, next class I ask for it.
Okay.
Hello, Ivan.
Yes, Mahesh.
I have used that command touch and a file name and then form. Then after that, I have to be type just paraform or
No, no. In your search, like you can click on the start menu and you can just type paraform or paraview. It will show paraview and then it will show like Ubuntu 2204, something like that.
after running the case, I have just put that command.
Okay, so wait, I'll share my screen.
Okay.
So suppose you have a case like this. I don't have a run case right now. So say I were to just open this.
Yes.
And WSL. OF9. And I would do touch, let's say file name dot form.
Okay.
Okay. So it has created, if you see over here, refresh. Yeah. So it has created file name dot form. Over here now, instead of file name, you can add anything you want.
Okay.
So now if I want to open this particular file, I'll go to search. Now, since your paraview does not open directly from the terminal, you can
Yes.
type paraview. It will give you a search like this. You can just open this manually.
Okay.
Yeah. So now once you've opened it, you can go on the left hand side under file and you can click on open, or you can just press Control O to just open your folder. And then you can go to that location that you have. Okay. Now
Okay.
mine would be under. Okay, I will have to, like, you can copy the path from here also on top. Let's say I copy this particular path.
Yes.
And I place it over here.
Could directly read that file into paraform.
Yeah, like, or you can manually just go to that whole thing. So now over here, I have it under Ubuntu 20, not under Ubuntu 9. I have it under Ubuntu 21.
Open from 9.
I run. And I had interface case. Yeah, so see, this file name is there. Okay.
Okay.
So I can click on open. And now since there's nothing in my file, so it'll give me an error. But once you've run your case, you can then open this file and click on apply. Okay.
Okay.
So this way you can open your files.
Okay.
Yeah.
Thank you. Thank you.
Okay. So if there are no more questions, we can close the session then. Can meet you then tomorrow.
Yes.
Today's recording will be available at what time?
Yes, today's recording tomorrow we will be able to give you.
Okay.
And it is already there in the YouTube link that I have shared. It was shared to you all in the email also when we have shared the joining link for this workshop. In the same link, all the videos are being live streamed, so it is there in the recordings.
Okay. Thank you.
Okay. So I think there are no more questions. So we are winding it up today. So once again, thanks you all for joining. Thanks to my team members, Paris, who was there in the first half, and Evan here. Manjil, thanks a lot. It was a very informative session. Yeah. Okay. So bye bye and see you tomorrow, 10:30 a.m. So please, many of you are joining around 10:20, 10:25. So please be there on time so that we can actually have more times for interaction and doubt clearing. Okay. Thank you. Thanks a lot. Bye bye.